Yay. All right. Hi, everyone. 59. 59 participants. Chat. Surabhi, Yash, Srirag, Harsh. Hello. Hi, everybody. Okay, so I'm going to share this screen and then we start. Oh, someone said good evening. I missed it. Chat. Oh, Vaishnavi. Yes. Hi, Vaishnavi. Good evening. Shamsuddin. Yes. Siddhi, Isha, Harsh. Got everyone. Hey, check this out. There's a new character that wants to say hi to all of you. He's got a he's got a turban cap thing going on with a feather. What's it with a feather? Okay. Srini says hello. Hi. Okay. So what we are gonna do is go back to our NoSQL databases one last time. Good evening. And finish up graph databases. So that is still one category. We started it, and then we just have to finish it. And then talk about MapReduce for a little over an hour, and then talk about data mining for a little over an hour. Again, we keep just rolling these topics until we finally finish them all. So we're in no hurry to actually finish. We get caught up. In the meanwhile, regrading, I guess the window came and went. So I hope you made use of it if you needed to. And I hope the final is easier than the midterm. Not that the midterm was hard. If you look at the rubrics, you'll admit that this is not a difficult exam, right? So you shouldn't call it difficult. Maybe it was unusual. Obviously, it's not what you're used to possibly, but I don't expect lots and lots of, long answers. Thanks, Vignesh. Once you know the answer, right, once they give you the rubric, it's very straightforward. Your mistakes are definitely made. Exam is one of those things which is not truly a reflection of what you actually know, what you can do. It is simply a matter of luck, timing, preparation. There's lots of extra variables, right? That are out of your domain. So just take it in stride. Like, don't be too upset. Don't beat yourself up. You're better than you think. Yes, it is definitely out of the box for sure, because life actually demands that. Okay, as more and more things get automated, is machine learning basically taking over almost every sphere of activity in the world. So the only thing that will remain is out of the box. Trust me. Okay, if something follows an easy pattern, a program is going to do better and faster than you. So you should get trained for that. Okay, so it's nice to think. Cool. So on that note, I gave you a spirograph equation, right? Yeah. Well, for the final, we'll try and fix that. This is a very interesting person. This is a map of Canada, a part of Canada. This guy has, a bike on which is mounted like a simple GPS, maybe his phone. So while he's biking, the GPS is collecting coordinates, just like you compute coordinates or just like you sample coordinates on the map. And then he just plots them. And purposely he picks paths that makes it trace out like a dinosaur. So he's a bikosaur. Okay, but that's who he is, a bikosaurus. And then we'll deal with this very, very important algorithm today called Hadoop. This is the reason why, yeah, TR, exactly. This is the reason why, right? Searching is so fast. How can you get like more than a billion results in under 1 second? I'm going to tell you. In fact, it's like this. So Hadoop is the public open source version of what Google introduced called MapReduce. This is MapReduce, okay? If you actually walk into Subway and you're ordering sandwiches, three people order sandwiches, then this is what actually can happen. So map, is when, what if so many of these things, can all be done in parallel, okay? So all these things can be done in parallel. Like somebody's doing this, somebody's doing this, somebody else, what. All these, servers, there are 6 servers. They're all processing all these 6, veggies at the same time. So it might take you like, 6 minutes, but in 1 minute they got done. So the speed up happens when you work in parallel. You chop things up and you slice bread. And then the combination is much, much simpler. You can do a little bit of this, a little bit of this. That is called reduce, okay, MapReduce. So there it is right there. Except now you have big data. So this like row. This is like row your boat. So like row your boat bunch of data. It's 40 billion, rows of data. So you want to do some calculation on all of them, the identical calculation. So why do them sequentially? Why not do them parallel? That is what mapping means. Mapping means do it in parallel. But then you'll have partial results that are not very useful. You have to combine them, and the combination to get the final result is called reduce. So this should be the same, whether you do this in parallel or whether you do this in sequence. You'll end up in the same place, but it can be dramatically fast. Cool. So the word parallel, if Google search through 400 or 500 billion pages they have indexed, one at a time, the word parallel will be here all night and you still not get done. But they're searching through like 100,000 machines in parallel. So it took over like 1 second and they got 6.5 billion results. Wow. That is how much speed up can happen when you do this. And then this is all related to that. So when you have a ton of data like that, you're trying to mine all the data and discover some useful business intelligence, then that can also be done in parallel. And so that is where the world of data mining and parallel processing, they all come in. Okay, they all come together. I don't think I have a lot in extras. Actually, I do, but maybe we'll come back to this, okay? Or I'll just tell you quickly. This is the new part, 1, 2, 3, 4, 5, 6. So please read them, okay? These two are very interesting. They're a company called Pure Storage. So they're like a data storage company. And here they talk about flash arrays for fast reads and writes. And then here they talk about this, conundrum. Should I back up or should I recover, or should I do a little bit of both? So read that. And then this one is about ETL. So here they call it reverse ETL. So it's a very interesting idea, reverse ETL. All the new things that I'm telling you are all because there's more and more data. So standard things like ETL don't fit anymore. So that's what that is. And then this is good old warehouses. How do they ensure no repetition happens? Right, yeah, exactly. So they partition the search index. Google will actually take the entire search database that they have and put it in all these different machines. And they have backups, of course. So in general, there's no overlap, no repetition. It is as fast as things ever get. So please read this because it summarizes all the things we went through, okay? But here, this one special company, that Supermetrics, they make some software that does data warehousing. So they talk about the schema, the star schema, but here it's all about things like Facebook, data, like Facebook logs. So if you actually go through this, then they walk you through all of these different places that you can collect data from and build a warehouse with all of this data. So if you're actually like a firm that, has advertising data, sales data, you need to care about like all these. When they come into your site, what are they doing at your site? Even all that metrics available. And then you just simply ingest data like crazy. That's what this is. Okay. But it's a very specialized application of data warehousing. And then once you have the data warehouse, then you can start doing queries on it. So again, this is how the real world operates. You should read that. Then a little bit more. So, this you should definitely join. All right, so Redis is a very simple key value pair database. You know that, right? That's all it is. Simply get put, how much more complicated then can there be? But they want to take that speed and simplicity and the versatility. It is all because of the same reason. The values are so gosh darn simple. But then they add the word fun, meaning that they're asking you, what else can you do with it? Maybe you can do some cool Instagram sorting, maybe you can 3D printing. It's all up to you. But look at that. So register and then definitely participate, okay? It's cool stuff. They're just giving you access to Redis and then they're asking you, what can you do? Okay, just go for it. If nothing else, right, you just get some exposure and who knows, you might win. So there it is. So US can definitely participate right there. So join the Redis Hackathon Challenge, okay? Why not? It doesn't cost you anything, just time. And then this is super cool. USC has always had a connection with Amazon. So in fact, there was a guy called Prem Natarajan. He used to be in the CS department. So he now actually runs one of the machine learning divisions at Amazon. And also our former chair of the CS department, Jared Medioni, he's a computer vision researcher. So he helped Amazon make the Amazon Go store, where you just walk in the store and cameras watch you all the time. You don't need any credit cards, no checkout. Just get what you want, put it in your bag and walk out. They'll actually charge you for it. So that is very cool that, USC has all those connections. Now there's one more connection. USC actually is being funded by Amazon to actually do like, NLP, like Alexa kind of research. That's what this is, okay? Some of you can actually do PhDs here. There's a brand new thing that is starting up. So he's the one that's heading it up. You can write research proposals. You can, like I said, join the PhD program. This is wonderful, yeah. It's going to put USC on the map. So get in touch with him. Just send him an email. He's in the EE department. I went to one in Seattle. Yeah, interesting. Yeah, I went to one as well and checked it out. I probably went to the same one. It's near those biosphere thingies that look like all spherical, right? Yeah, it's in downtown Seattle. It's very interesting. Yeah, the secret thing, I'll actually go through this in class. Some of this we definitely know, but our CS department actually work with them. Yeah, they pretty much, track your hands and then they track what product, came into your hands and what product went back. So you can actually take something and put it back. They wouldn't charge it for you. And then they know what you picked up where, and then they charge you. Okay, so we'll go through this another time when we talk about machine learning. The reason why we talk about machine learning in this course is because the machine learning that is popular in the world is called supervised machine learning, which is pure data. Unless there's data, there's no supervised machine learning. So it is all data driven, which is why we can talk about it. Okay, so roughly about 10-15 minutes and then the rest, okay? So this would be a fast review. We won't go through like what we did before. We'll end up at the very end pretty soon. So SQL is still definitely around. It has, newer syntaxes, slightly different syntax, but overall the same. Select something from something, where something, that didn't go away. And then JSON is really the bottom line, because everything can be stored not as relational tables, but completely unnormalized long column, meaning long key value pair JSON. So everything is in one place, and it's trivial to convert RDBs to JSON. I'll mention something else in a while. I still remember. So on Facebook, there's a group for generative art. So generative art is program-based art. So there's a researcher that actually wants some help in loading some relational database from a site that has Japanese data. So some of those characters that are stored in the tables are actually Japanese characters. So if you know Japanese and you want to work on this, so what he wants is all the table data to come out and then live in some kind of a simple NoSQL database, which will then animate a whole screen. So the screen is going to have this cool animation, but all the animation is in JSON that's being driven by a relational table. And they pay you for it, actually, you can get paid. So if you like, you can mail me and I'll hook you up with that person. Anyway, so that's what this is. You can easily take data from relational databases. And then once you do that, same thing with XML, you can easily convert XML to JSON as well. These newer databases are not consistent immediately. You don't care about consistency. You worry more about the fact that they're up all the time. You never take them down. So it's a different way to operate. But if you want, you can still hold on to your relational data. It did not go away. So you can still have the old world, and this is the new world. So we've gone through 3 of these, okay? So about half of this. Again, this is simple key value, and here you operate more in terms of columns. There are more column queries, but groups of columns. And then here it's more general version of key value. The values can be extremely complicated, but then the API allows you to access any value at any level. You don't have to manually search for it. Here you have to search for it. And then in graph, all of this goes away. Every single key value can be separate, or a bunch of key values can be separate. We call it a node. And then it's all about how nodes are connected to other nodes. So that's the most general thing that there is. So we talked about that. All right, so this whole key value, the Redis challenge that I mentioned is a key value database. And then column databases can be used for inverted indexing. I told you to look into that. Facebook also worked on it. And then DocumentDB, so the 2 big ones are Couch and Mongo. This is what most people think of as NoSQL. And so those are called documents because they can store pretty complex, nested forms of data and then still be able to access any comment. You can say, give me all the comments posted by Sati last year. And then it can go to every single blog post, see if I commented and see if the date matches the range, and then give me the comment. So stuff like that. And then I showed you, then here are about graphs. So in graphs, you take your tables, but then every single cell or every single row actually can become a node. And then all the rows can be connected to other rows. So that's all very cool. And then there's so many graph database companies. And then, like I said, ultimately what is in every node is data. Also, the edges can have their own data. And so there's data on edges as well as nodes. And then you can query them all. And so talking about querying, the query language depends on the database. For Neo4j, that's one of the more common graph databases. It comes with a custom query language called Cypher. And so this is classic SQL, and then Cypher is much simpler. But I told you, rather than learn Cypher, learn something else called Tinkerpop, because this is portable, because every vendor thankfully implements Tinkerpop. It's almost like a graph database version of SQL. Someday it might become the standard. So I give you like all kinds of resources for it. So this might be the newer part, right? How do you specify a graph? And I think we talked about this a little bit during the discussion, meaning, or you can look it up, I'll just tell you. So a graph exactly is this. So what I'm asking is, if you are given any graph, I'll just go back to this graph as an example. How would you use JSON, actual text JSON, to make sure that all this data is represented, so that if somebody then were given just the JSON, you're able to get all this back. So in the JSON, you will have a node, and you'll have a node ID, node name, node age. So you'll have maybe a whole array of just nodes. Node can be an array. You can have a different array of just edges. All the edges can be a separate list. And maybe every edge can have an ID, like A, B, C, D. And then you can have a third grouping that says edge A connects node A and connects B. Edge X connects node B and node C and what. So you can have all of this described as separate JSON. Please think about how you do that, okay? I'm giving you a practical problem. And there's absolutely more than one way to do it, okay? There's many ways to do it, but think of at least one way. So that again, the answer would be, I would give you the JSON. You might be able to read that and even draw me the graph that I showed you in the other slide. You completely capture the whole graph. How would you do it, okay? Think about it. But in the meanwhile, The world uses something called a dot notation. This actually precedes things like JSON. It's a dot language, and it's very cool. I'll just show it to you. This is the BNF grammar for dot language. By the way, speaking of BNF, speaking of Turing Award, all of that, today the Turing Award was announced for 2020. Ha! This is a textbook that we've all used. Aho and Ullman. Ooh, the Dragon book. So, right? Algorithms, even data structures. That is exactly the two people that won the Turing Award for the pioneering contributions. So it's not that they won the award for writing textbooks, but they are the reason why modern day compilers exist from a higher level language all the way to assembly to machine language. Okay, so amazing people. Anyway, so their work builds on stuff like these, the BNF grammar. I'm going to keep going. That was the grammar for dot specification. This is ultimately what it is. So A, arrow, B, C, okay? So this means there's a node called A, there's a node called B, there's a node called C, 3 nodes A, B, C. A is quite connected to B, A is also connected to C. That is how you write it. So, and then there are drawing programs that can read that data and then plot it for you. So this just keeps going, okay? This is the language, but then I'll show you something more visual. It's like over here. So what can you do with it? There are practical drawing programs. There's something called GraphViz, for example. So in GraphViz, again, you take the graph notation, and then turn it into this. So an exam question, believe it or not, that I might ask you is I would give you this and say, how would you convert this to JSON? Right there, how would you convert that to JSON? So that whatever is captured here would now be standard JSON with a curly brace and a curly brace. And then you can write a different viewer, you can read the JSON, produce the exact same graph. Okay, so we don't need this custom language anymore. So please think and please read. Just more of the same. Dash means edge. Okay, you figured that out. And then a directional graph is called digraph. So A, arrow, B means unless B is connected back to A, unless it says that this is a one-way connection, like one-way street, you can just drive around. Okay, so and then you can have a graph, an edge onto itself. That's possible. E is back onto E. And then labels. So these are extra key value pairs, right? They can go on it. So please think, okay? This is an entire language. It's beautiful. And then you can have subgraphs. You can even have a little subgraph. People that write research papers might actually produce something like this to include in a paper. But what if this is all replaced by JSON? That would be my question. Likewise, there's an XML-based version, a little bit better than dot. There are actually 2 XML versions. One is called GDF, and then the other one is called GraphML. Please Google them, okay? For example, if you search GraphML, I'll show you the picture. This is an XML-based way of describing graphs. And then once you describe the graph, you can draw stuff like this, okay? Again, the idea is how would you use XML? Again, an exam question might be, I would give you the GraphML for this, and I would ask you, what's the JSON? Or just simply Google it, like the way I'm doing it. But for one of them, I'm going to show it to you. So the GDF one is right here. The GDF one is, this was actually from HP, from Hewlett-Packard. Yeah, GraphQL is a very different thing that I still hope to tell you about. Loosely yes and loosely no, okay? Like GraphQL does not need any of these, but GraphQL could use these if it wants, that's all. Okay, so in the meanwhile, out of HP, came out a language called Guess, and so here's Guess. If anything, you can even take your spatial data and then make all your X and Y values, latitude, longitude, be actually one of these Guess grammars, so that it becomes like a spatial database, and you can take your convex hull that you computed and actually make it a graph layer. So many things that I tell you that appear unrelated, they're actually not unrelated, okay? You should actually make the connections in your head, because that is what I quiz you on. So again, this could be the USC campus and students, how they're connected to each other, like physically, meaning geographically. Okay, so there's so many things about the language. Just know the basics of what Guess is. You don't need to know all the details. I never asked you about details. The overall point of all of this is when you have a graph database, a real world graph database, there's many different ways to specify the database before you search for it, including Tinkerbob is one more way to do it. Okay, now on to a very different topic. This is more like an AI kind of a topic, a triple store. Okay, so a subject, predicate, object. Now maybe I should draw very quickly. This is actually extremely important. What it is I'll run this. Okay, every piece of knowledge, every experience, every memory, every scientific fact, everything, anything, every what, okay? Anything that people have in the world so far that humanity has ever created can all be described using this pretty amazing idea called a triple store, okay? And a triple store could not be simpler. It's like just a basic idea. It works like this. So in a triple store, you say something. For example, USC. Here is LA. Draw a little arrow that says USC is located in LA. This is called a triple store. Okay, so this is subject, and then this is the object, and this is called the predicate. Predicate is a property. Okay, so subject, predicate, object. Likewise, you can have UCLA. UCLA is located in Los Angeles. Caltech is also located in Los Angeles. The Keck Memorial Hospital is also located in Los Angeles. USC operates Keck. JPL is also located in Los Angeles. Caltech operates JPL, and on, okay? So you very quickly see how complex and beautiful this can be. So Sati lives in Los Angeles. Sati teaches at USC. Sati lives near Caltech. Sati has visited Caltech. So there's no end to what you can do with all the data in the world. You can link them all up. It is just wild, is what it is. So that is called a triple store because it's triple, A, B, C. In other words, A, B, and a wire between them describes what the relationship is. There can be many relationships between two things. I told you, me and Caltech, I live near it. I also, visit there. Okay, and I've attended talks there, and I have friends there. So they're all different. Well, a predicate is a second value. It's almost like A linked to B, so B would be predicate would be its middle part. So predicate means the property. In other words, what is the connection? Okay, that's all it is. So because again, when you say USC LA, like why do you mention it? Because USC is located in. Okay, so that's the connection. Okay, so to your point, normally when you describe data, the nodes are more important. It's almost like the edges are not very important. But here in a triple store, it's called triple because ABC, there are three things. The predicate, the edge, is just as important as the nodes themselves. Okay, so that is so cool. Okay, so that is anyway, it's called a triple store. And a triple store has a very specific XML format for storing that makes databases, be able to search them. It is called Resource Description Framework, RDF, okay? So RDF triple is sometimes what we call it. So there are commercial products called RDF databases where you can take the little graph that I just made and actually make them into real RDF triple. And then somebody can go searching for it. Somebody can say, go to a node called Los Angeles and find all the universities that are located there. You can also, by the way, tag nodes like, UCLA. You can have extra properties. UCLA is a school. USC is also a school. So tell me all the 4-year schools in Los Angeles. You can do graph searching basically. So it's a form of a graph database. But it's also AI in the sense we can take all the knowledge in the world and then we're able to store it as just these tuples. And it's a directed relation because A links to B. In other words, the subject links to the object. The object could link back to the subject, but it's usually a one-way thing, right? Like USC is located in LA. You can say LA holds USC, you could say that. But in reality, it's just the same thing as USC is located in LA. So it's a one-way relationship, this predicate rather. Okay, subject, predicate, object. I'm going to give you a few more examples. And then occasionally you can have a timestamp, a fourth value called a timestamp. And then you call it a context. Then if you have 4 things like that, a timestamp, then we call it a quad store. And then sometimes you call it a name graph, okay? You can even have a quint. So in a quint, you would have one extra attribute called a name or an ID attribute. Okay, so ignore things like quints and quads. We usually only use triple stores. So in a triple store database, the query language is called a semantic query because you're not searching for keywords necessarily. You can actually search for actual relationships, the meaning between all that data. So it is a form of a graph database. And it's restricted because all of those arrows are only one way. You cannot have a bidirectional link. And also you cannot have things like hypergraphs, they're basically just standard, A links to B, something else links to B. It's always, A arrow B, A arrow B, arrow B. But except those can all not be loops, they can all be hooked together, okay? So it's a form of a graph database. All right, so here it is. Again, it's a bag of triplets is what we call it. Supposing there's a graph that is here. And then each graph has got this specific format. It's called a triple, and some kind of triple's ID. And then this is the triple's node name. So this is all about somebody called person, okay? It's all about person. But about each person, about the person called person too, you describe so many things about the person. The first thing you describe is what do you mean by person? This person. So the word doesn't matter anymore, the type matters. And then what is that person's first name? It's Rose. What is the person's middle initial? So these are all like column values, column names, and these are actually cell values, okay? So this way you fully describe the person. When they were born, when they died, and then they're a female. But here's the cool part. This person has a spouse called person 1. So if this was all a node called person 2 holding all this data, all these triples in right there, or even wires like this. So say there was a node called person 2. So I guess what I'm saying is there was another word called Rose. Then you can say the person's first name is Rose. Suppose there was a different person. The name was also Rose. then they would have a very similar relationship. But the other person whose rows is not person 2, it's person 20. Then you can say show me all the people who have all rows, okay? You can do that. So these are all different nodes. These are all the same node. But now this node called person 2 is now pointing to all of these nodes. That's what this is. But among all the nodes they're pointing to, one more node happens to be called person 1. And the wire that is pointing is called spouse. So that'll be a bidirectional relationship, because from person 1, you have a wire back to person 2 that's also says spouse. So I'm your spouse, you're my spouse. But now person 2 can have more things pointing to, like where they work, or what the friends are. So you can see how complicated this can be. And then now person 2 has children, so has child as child. These are all dependents. Hopefully person 1 would also have the exact has child as child as well, because maybe person 2 and person 1 had all these children together. Unless person 2 was married to a person 3 and had half of them with a different husband. All kinds of things are possible, you guys, but you can see how powerful this is, okay? You can just endlessly grow this. There's something called 6 degrees of Kevin Bacon, right? You might have heard of it. Somebody might not have heard of it. Okay, so 6 degrees of separation. Because Kevin Bacon, and he basically mentioned this, he said, any 2 people in the world, if you start finding out who their friends are and who their friends are, you will only have a maximum separation of 6, meaning between 6 hops from one person to another person, you can link any 2 of the 7 billion people in the world. That's basically what he said. Interesting, right? It could be true, it could be not true, but there's all kinds of games you can play, like stuff like that. So then that is his notion, see, like that, any 2 people in the world. Hard to believe, but it's probably true. So that can all be searched. Things like that can be actually searched in a schema like this, okay? There's no schema in the sense the schema, this is the schema. It's always like an object, a subject, and then some kind of an object, and then some kind of predicate. Predicate is the wire between them, okay? CJ does answer the question. These are all predicates. And then these are all objects. They're targets, more like subject and a target. But those targets are also nodes, and then they can have more predicates and so on. So it endlessly just grows, okay? All right, so then what are the companies that actually make this software so you can actually try it? So here are 4 of them, and you can Google them all. They all actually have free versions you can get, and it's very cool. There are all kinds of sample databases you can get, RDF databases, then you just try it. So then to that point, how do you query it? You can query using many query languages, that RDF format. So then see they all end with QL because many of them actually seem like SQL, okay? So this is pronounced Sparkle, like sparkling. So Sparkle is the most popular. You can even Google like Sparkle RDF examples. You can actually see it, okay? So like this, just say Sparkle RDF in example. And it's very simple. So once given an RDF database, and then even TripleW, has their nodes all being described by RDF. So there it is. So what does the query look like? Architecture endpoints, friend of a friend. Okay, so this all gives you, more syntax. Okay, see like that, give me all the properties, See, it looks so much like SQL, right? That is actually how you query in Sparkle. See, where person, friend of a friend. So in other words, this is the relationship you look for. So for a person, then you go through all the wires that link the person to so many triples, and you look for that kind of triple property, and then you look for the thing on the other side. So you're looking for the person's email, you're looking for the person's name. Cool. So it's a lot like SQL searching, but now you're going from node to node. Specifically, you're going from RDF triple node to another RDF triple node, meaning you're jumping between subjects and objects. So this just goes on and on like that. Yeah, then the output, that you get from the query can be a graph because you're actually asking for what is connected to what, right? So then you can make a small subgraph out of them. So it's as if the whole thing was one massive graph and the result is a subgraph, which is like when you have a table and you do a SQL query. So unless, you're not talking about column operations, the result is another table. Likewise, the result of a graph is a smaller graph. It's a subgraph. Cool. So then you can make all kinds of, chaining inferences. You can say for this person, name all the friends, and then for their friends, name even more friends. And therefore the friends name the enemies. So you can actually do like chaining, some logic inferencing. And this is how you can very simply represent stuff, okay? Suppose humans are all mammals, okay? So and then suppose you say, man is a subclass of human. Then you're asking, is man a mammal? Just very simple little, connection between them, just linking. So trivially the answer would be yes. All right. So Wikipedia itself is one massive RDF triple. Wow, that's pretty cool. In fact, it is so big that you couldn't even download all of it. You can actually download parts of it. It's all free. You can get it, okay? So like this. You can just get entire Wikipedia because all of those links are exactly what are the triples. Say you have a page about US and say you have a page about Russia, and there are many, many links between them. One link might be Cold War enemies. So then that becomes like one of the wires that's here in DBpedia. So they take every link in Wikipedia article, linking to every other article, and make them all into a ball of like RDF, triplets, okay? It is so cool. Look at this. Just download them, okay? Get this massive zip file. And then there's all kinds of visualizers. You can load them into one of the graph databases I named earlier, like Allegro Graph, and run these Sparkle queries. Just do it. There's endless homeworks I can make, but then the course would never end. So I'll just tell you, just grab this and then put it in one of these, and then learn a little bit of Sparkle, and then see if you can query things yourself. That's all you need to do. All right. So then triple store DBs, again, they're slightly different. You can have DBs that actually store RDF, a very special XML format, or you can store them in any kind of native format that the vendor comes up with, because they're just going back and forth. That's all. All right. So therefore, RDF, the XML part of RDF, the storage format is called N triples. Okay. So RDF is more like the language, like an abstract language. But in reality, you store RDF data, like these triples, in a form of what are called N triples. So N triples look like this. It's pure XML. Okay. But then there it is. So, there's some kind of relation between them. Okay. So person, and then, there's another person, and then there's a maker, relation. And then like this, friend of a friend, they're like friends. And then the quad, probably like a predicate, so there's a context somewhere. But that XML is what would be exactly like one simple connection between a subject and an object using a predicate. So it's obviously a little verbose and painful. So maybe this should be replaced by JSON someday. But because it is so specific in terms of all these tags, a machine can go looking for the connection between them and then just start doing queries. In other words, it is a way to describe graph databases. All right, so all this, and then every tuple store is an RDF, and then here's a small graph. Right, so suppose you have a barber shop, okay? Just to give you a little practical example. So then that's from here. So you have a barber shop, and then customers come, right? And then barbers serve the customers, and then customers pay some money. Things cost certain money, almost like a dental homework. Then if these things are all described as a bunch of RDF triples, then you can ask in any given day how many haircuts were performed. Add up all the dollar tens, add up all the ones that say haircut, and then maybe add up all the value. How many people did a barber called John service, or who was serviced by, or Jim was the customer, so who actually serviced the customer? You can go looking up all of these because somewhere the data is in there for all of that. Okay, so again, you can see what I'm saying. The things that I'm asking, they're all like two at a time using these relationships. So these would be the predicates now. So Jim went to the barbershop. So Jim got up in the morning, and Jim did other things as well. Went to work and bought coffee, but then he went to a barbershop. So if there was a timestamp here, you can say, who are all the people that went to the barbershop? Hopefully Jim would be one of them, because so many others also would have the same relationship. Okay. So again, these are tiny, little pieces of data, but you can hook them all up together. Okay. So N triple files are called .nt files, and then here it is. Okay. So you can actually have like this. So the cost of a haircut is $10. Again, that's the key, that's the value. And then when did the haircut happen? Who was the service provided by? And on and on. Okay. So then if you want to play with all of this, a free way to do it is called RDF4J. Okay. So it's like a jar file that you can get, and then just play with it. Just load like an RDF into it and then do some search on it. Okay. Just FYI. In the future, these might be popular. And then how do you actually, set up to run them? In other words, how do you actually store the data? Like, what do you do with it? One way is because triples are so lightweight, you can store them in a key value database, like a main memory database. So those are called in-memory key triple stores. They're very fast, but they're pretty expensive because main memory is expensive. Or you can actually use a native store, meaning every vendor, they have their own format. So this is not RDF, but they have their own format for storing the triple somehow. And then when you go and run their software, then they'll load the triple that they have in memory, maybe using some binary, some encryption or something, or compression. But then they know how they store it. They know the format. That's one way to do it. So one way, second way. Third way is you can actually take those triples and put them in good old relational tables. Wow, that's very interesting. So if you had access to all the relational tables, you can forget all this and then straight do SQL if you want. But normally that's not done. Normally you have a front end that makes it seem like it's all graph triples. But at the back end, they're actually using a relational database, okay? Then it's called a non-native store. Native meaning a graph is actually stored as a graph. The triples are stored as triples. But here the triples are stored as column values, right? So column A, column B relationship, what. So therefore you can just fill like randomly 3 columns by using column A for subject, column C for object, column B in the middle for predicate. but you're using tables, and tables are not triples. So then it's called a non-native store. Okay, so that is how we end our discussion about graph databases. Okay, so again, to summarize, triple stores are a very special kind of a graph database because you're making the whole database 3 things at a time, 2 nodes connected by a wire. But the idea would be that if you do it enough, then basically all the nodes you ever want to connect, they'll all get connected. So if this was done using a triple store, then you would do it that node, that connection, this node, that connection, this node, that connection, that. So you would store this as 6 different relationships, okay? But then in the end, you store them. It's always basically 3 at a time, meaning 2 nodes followed by a wire. Same thing in here. You'd have that as 1 triple, 2nd triple, 3rd triple. And if these 2 departments collaborated, there would be 1 more triple called collaborate, and so on. Okay, so things for you to think about. And then go backwards. So graphs are extremely powerful. Graphs are the most powerful thing that there is because there's almost no structure whatsoever except for the structure that you described. So there's no documents, there's no nesting, no hierarchy, no tables, no key values. It almost appears to be nothing. It is too wild, but there is something. All those relationships are what are those something. So if you then know how to hop from node to node based on what relationship you're looking for, it seems like this can do everything that everybody else can do. And that is the truth. Using a graph database, you can mimic relational databases, you can mimic simple key value pairs, you can mimic documents, you can mimic column databases. Because in the end, they're all in the abstract, just graphs, okay? Nodes and wires. So looking forward to the future, will be the graph database is the most general kind of database that there is. All right. So now without missing a beat, we're going to say, what if you have a massively large graph? What if you have a key value database that is, again, 1 billion rows long? What if your documents like in medium.com, right? Medium has millions and millions of articles. So how do you then go looking for all the comments that Citi made last year in any really reasonable amount of time? You need some fast way to search data. So that is what this notion of MapReduce is. Okay, it's a very special algorithm. I gave you a little meme at the beginning. We can go back to it. That algorithm is what I'm going to describe to you in a little bit more detail. So if you understand how this parallel operation works, this is future proofed because in the future you might have 10 times, 100 times more data we have today. It is pretty much unimaginable. Maybe you store data in quantum format like in atoms. You store data as holograms. Maybe you store data as DNA. You store data as laser beams. We have no idea how the heck we're going to store all the data. But after you store the data, next problem is, oh my God, how are we going to search for it? This is the answer. It's like almost infinitely scalable. There's no better answer. You mentioned everything in the world is a triple. Yeah, definitely, absolutely. You can store any data in the world in a GraphDB, correct? That's exactly right. The others are more like structure, So if your structure is pretty straightforward, then a graph is too loose of a structure. This could run faster, That's the advantage. This one is too basically broken up, It's hard to parse the structure. Here you already have an import structure, and maybe you can make use of the structure here somehow. Like at least walking through all of the data, you have a hierarchy, exactly what you're looking for. Like a blog post on Medium, right? It always looks the same. There's always a title, there's always somebody that wrote that, there's the body of the post, and then there's claps and comments on the side. So that structure, is here. Here, the structure is much, much more loose. There's almost no schema at all. That's all. But that could be an advantage or a drawback. The design is more loose, is the best way to put it. It's more organic, meaning if you're not careful, it might be hard to find what you put there. So maybe not complicated, but more like less structured, like less principled. It might make, if you're an OCD kind of person, right, it'll drive you crazy because there's almost no structure. But the data is all there. Yeah. Right. So scalability can be an issue. Yeah, sure. Again, because, the graphs. Okay, so I'll tell you one actually good answer, which is actually tied to this. The one thing you can do with documents that you actually cannot do with graphs trivially is this. If you have 1 million Medium posts, right, million Medium articles, then I just told you how you can search through all of them very quickly. Suppose somebody made all of the documents, those Medium articles, and made them into graphs. Searching in parallel is not so simple anymore. I'll just quickly visually tell you what I mean by that, then I'll tell you more later on. When you have a graph, okay, so just to back up, when you have 1 million Medium articles and I want to search through all of them and say, what are all the ones talking about JavaScript? What you do is this, just right here. You take 1,000 Medium articles and you put them in this server right here. Another 1,000, another 1,000, 1,000, 1,000. You have 1,000 servers and each has 1,000 Medium articles. 1,000 times 1,000 is 1 million. Remember, you have 1,000 machines, okay? You run a search query on each of those thousands all at the same time. You tell every single one of the 1,000 servers, Go through every one of those 1,000 articles that you hold and tell me if the tag or the subject says JavaScript, and if so, give me the name. All the 1,000 run in parallel. That can be 1,000 times faster than they're all running one at a time, okay? 1,000 times faster, remember that, okay? 1,000 times. Or even in the most amazing case, suppose you have 1,000,000 servers and you have 1,000,000 Medium articles. Each server gets exactly one article. And in the fraction of a second, right, it's done looking through and it's telling you, is that article JavaScript based, yes or no? 1,000,000 times faster than running all one at a time. Amazing, right? Okay, so that is possible because it is so easy to take your document cluster, meaning a list of all your documents, and easily distribute them. But if you make them all into crazy graphs, right? Suppose you have a word called JavaScript and so many nodes are linking to JavaScript. You cannot partition a graph easily at all, because once you break the wire, then you have to pretty much duplicate the wire on the left-hand side and the right-hand side. So partitioning graphs is not trivial at all, okay? That is the simple answer. So it becomes a little bit of an issue. Right, exactly. So that's true. You probably wouldn't do what I said. Yeah, you're right. At a certain point, if you overdo it, then combining can be a problem. There's usually a sweet spot, maybe 1,000 times 1,000 is good. All right, you guys, so that's pretty much it, okay? Yeah, he's saying the same thing. It is very easy to take because every document is self-contained. A graph is by definition not self-contained. It's like all over the place. There would be a node called city in all the articles that I wrote be pointing to me. So it's not easy to partition a graph, that easily, but documents are easy to partition. All right, we should move on, and I'm going to tell you more about MapReduce. Between the mapping and reducing steps, this is a step, this is a step. This is a parallel step, this is like a combination serial step. But this is the one that takes a lot of time. This doesn't take a lot of time. So we try to parallelize this. But before this can happen, in between is an invisible step that never even gets pressed, meaning people don't talk about it. It's called the shuffle step, okay? We take it for granted. See, in reality, it should be called map, shuffle, read. Sorry, map, shuffle, reduce. I guess Google thought about it and said, that's a mouthful. We don't want people to say map, shuffle, reduce. We'll just call it MapReduce. But always know that there's a shuffling step, okay? Then if you say, what is that? It's really big data processing at scale. At scale means not a sample of just like 10,000 documents. The whole thing, the entire Google index of 1 trillion documents, is that sort of thing. How do you do this for real? How do you do big data processing for real? The word MapReduce is not used so much these days. And then the idea of mapping and reducing might also not be used as heavily as it might have been in the past. But even 20 years from now, you can dig it out, okay, and still use it. There's nothing wrong with it, but there might be other ways of doing it these days, like, stream processing. All right, but the MapReduce idea never went away. To read through this, it's a computational machinery. It's an operating system. People call it like a distributed operating system. So when you have a bunch of files, they can even be scientific data. It can be any kind of data, at all. You want to operate on them in parallel. What do? You do MapReduce. MapReduce replaces supercomputers from the past, because in the past, supercomputers had two things. They ran pretty fast, obviously, but they also had what are called vectorized operations, meaning in an array, suppose you want to divide every element by 2. Normally, you write a for loop, for each. But if you take every array element and then you put them all on different processes, you can tell all of them at the same time, divide yourselves by 2. Those are called the vectorized operations. So these days, you don't need the vectorized operation and the expensive supercomputer like a Cray YMP. Instead, you can use it as a MapReduce operation. So it's become a parallel processing internet platform. All right, so this is all possible. Again, underneath MapReduce is the assumption that there are keys and values, good old JSON, okay? Okay, the keys are what makes so many things possible. So I'm going to show you this. And then traditional machines absolutely cannot work. I told you, what can you think of in programming using like C++ that can make something 1,000,000 times faster than what I can do? Nothing. There's no such thing. But you can actually massively parallelize it. Again, the Google search is the answer over and over. Ask yourself, how does it work? It works like this. For Google, it was basically an existence crisis. Unless they came up with something like this, Google was going to go out of business. This is called SIMD parallelism. So I'm going to draw a little bit about SIMD, okay? So SIMD stands for single instruction, multiple data. Oops, maybe I should write it differently. Okay, wait. So I want right in this part that has text in it, okay, but I'll grab it, okay, because it's easier to do. Okay. So SIMD processing looks like this. Suppose you have an image like this, just like my desktop right now, but my image is massively large. It has 12,000 pixels by 8,000 pixels, much bigger than my screen right now. And it's a massive picture that I took with a large camera that I have. I want to brighten this by 10%. The image is too dark. I want to go into every pixel and make the pixel be brighter by 10%. Remember, I have 12,000 by 8,000 pixels. Okay, that's like many million pixels. It's going to take me a long time when I open up Photoshop, or if in View, probably like, an hour. But instead, imagine if I could somehow partition all these pixels into 4 parts, and I grab all of these pixels and I put it on one processor. And then all these pixels go on a separate processor. All these pixels go on a third processor, fourth processor. And I run Photoshop or my image processing application on all those 4 machines in parallel. And I tell each of those machines, take all your pixels and brighten yourselves by 10%. So they all get done. But if you stop, I don't have a new image anymore. I have 4 sub pieces, right? So I need to combine them. I need to bring them all together and tile them very trivially and put it up on my monitor. Wow, I got a bright image 4 times as fast as what I can do. What if I break it up into 16 parts? What if I break it up into 100 by 100 parts? This becomes arbitrarily unlimited parallel speed up. The more processors I have, the more I can do in parallel. Single instruction, it's the same instruction over and over, same brightening operation, multiple data. This is separate data, that's separate data, separate data, separate data. This is exactly what we do in MapReduce, okay? So in MapReduce, when you have a large table, USC students, 40,000 students, I want to find who has the lowest GPA in the entire USC, sad for them, and who has the highest GPA. Just imagine it's one person, okay? You want to find them, or maybe the person that makes the most money in the US, Jeff Bezos, and then who is the one that makes the least money, maybe $0. So you have 300 million people. So then the way to parallel process is you break them horizontally, you do horizontal sharding. So you take groups of data, then you put them on one processor, second processor, third processor, fourth processor. Go back to a GPA example. If you want to find the lowest GPA, highest GPA, run the lowest and highest operation on each machine in parallel. So each one would give you lowest, highest, L1H1, lowest, highest, L2H2, lowest, highest. Now you need to reduce them. How would you reduce all the lowest into one lowest? What do you do? I have 4 different lowest values. How do you reduce all the highest into one highest value? Suppose I have L1, L2, L3, L4. What do you do to find the lowest of all the 4 of them? Just a simple little operation. What kind of operation finds, the least of 4 floating point values? Suppose this server gave me, somebody got a GPA of 1.2, and this person has, 0.4. That's even possible. Okay, somebody has a 0 GPA. L1, L2, L3, L4. These are partial answers. So how do you reduce those 4 partial answers? What is the operation? Min, right? So just simply min, yeah, exactly. So do the min of all of them. Likewise, if you want the largest of the 4 sub answers, find the max of them. Maybe all the 4 are the same. They're all 4.0. It doesn't matter. Just find the max, okay? That is pretty simple compared to searching. So that is the idea of MapReduce. So this is called mapping in parallel, and then reducing, just a simple operation. Cool. Okay, so now that I've told you, sometimes the reduce also provides you a reduced version of data, but now you want to do more operations. So then you can even take all of this data and put it in a second set of mapping operations and do something else in parallel to them, and then you can reduce them. So in general, the MapReduce can be in stages, okay? So MapReduce first stage, MapReduce second stage. In scientific calculations, you can do multiple MapReduces. But regardless of what you do, it is all much simpler, much faster than doing it all sequentially one after the other. That is the biggest parallelism that we get. All right, so now we understand SIMD, okay? Single instruction, multiple data. There's something called MIMD, by the way. So in parallel processing, there's something called MIMD. That is not what we do here. All right, so functional constructs, MapReduce. This word map is an operation. It's actually a function. It exists in Python. It exists in JavaScript. So the map function, in fact, I'll show you right here. The map function takes as an input a bunch of data, say an array of data, and then an operation to operate on the array of data. Like I said, maybe divide by 2 operation. That operation is also coming into the map function in the parentheses. In other words, map is not just given an array of data. Map is also given the function to run on the array of data one at a time. In this case, the divide by 2 function, or search for the min GPA function, or find all the words that begin with the letter S function, or find all the people with cancer genes function. Think of parallel processing big data, or find all the spots in Los Angeles, find all the XY coordinates that are just within the LA boundary. Those are all functions that you write. So those are called mapping functions. This map function does not know what those are. They're just coming in as an input. The job of this is to simply distribute all this massive data and run that function that you supply on as many of clusters as possible in parallel and quickly give you a result, okay? So a function that takes not just the data as input, but also another function as an input is called a second order function. Filter is also second order function, reduce second order function. When you have functions that accept other functions as an input, those are called functional programming languages. And like I said, Java does it, JavaScript does it, Python also does it. Okay, so map is a second order function, so is reduce. Filter is not used in big data, but they always go together because, you know, this does something very similar. So I'm going to show you examples, okay? Before we do map, filter, reduce, those functions that come into map or come into filter, come into reduce, they can have a separate name in JavaScript. I can name a function parenthesis v curly brace, you know what. Or those functions are throwaway functions. We don't ever going to need the function after we finish through map. So those functions can be anonymous. They're called, you know, serverless lambda functions. That's what this is. So here's an anonymous function, you know, this in Python, okay? So what happens is this, here's the Python shell. I can even like do it right there. You say this, you say, I'm going to write a function called this. The function has no name. Normally this would be the word function, right? This would be def in Python. Then some function name like add, add, but no function name, but instead you say lambda. These are the function arguments, function inputs. Colon, there's no need for curly brace, all that in JavaScript, you know, colon, functions output. Input, colon, output. This is as simple as a function definition can ever get in the world. You throw away all the unwanted stuff, including function's name, not even the word return. Anything after a colon is considered return. The functions must return something. That's it. And then you call the whole thing lambda. All right, so this is an anonymous function, but then how do you call it? You can call it right here, but it's more suitable to store that in a variable. This is not the function name if it ever came up in an interview. F is not the function's name, okay? The function never had a name. F is just a pointer to it, it's a reference. It's a variable that is holding that function. But it can pretend like it's a function's name because now I can pass data to it and you'll get to, okay? In the end, you're just storing a handle to an anonymous function. That handle can be passed to a map function. Now you understand, okay? Like this. So in the map thing in Python, the function comes first and then the array comes afterwards. So let's run a quick example, okay? Like this. Oh, no way. I'll actually get it. Okay. How do you, okay, let me actually do HTTPS. Wow. I thought that's what I tried. Do you do it here? Somewhere it says you can allow, right? So does anybody know where that happens? We don't want to do all of this. That is crazy. Okay, it doesn't matter. I can actually go in Glot and do it myself. That is pretty bizarre. Just purely for fun, I'm going to see what happens. Okay, just very quickly, okay? If it doesn't work, it doesn't work, but it's worked in the past. Okay, odd. Normally you give it permission that says it doesn't matter, just run it anyway. Okay, let's do this. If it's not Glot, we can do it somewhere else. Okay. Oh, wow. I should do an exclusion. Oh, come on, and I'm not going to bother with all that. Let's actually go to glot.io. Let's do it right now. Okay, Glot is a polyglot programming language. We'll never go to Glot. Okay, what else can we do? We can do REPL it. Yeah, right. My malware is actually, yeah, it is. I don't want to turn it off. I'm actually scared. I'll leave it on because then I'll forget to turn it back on if I turn it off. Oh, man, everybody. Okay. I'll tell you what we're gonna do it. Let's actually do it in JS fiddle. No, that's JavaScript. Okay, one last time. I'm gonna say online Python IDE. There's many of them. Okay, online Python shell. Okay, program is online Python Kunji. Let's do this one on GDB. Okay, finally, here we are. Let's actually get this. So what I'm trying to show you is something very simple. Suppose you have an array called Celsius, okay? This is your big data. Imagine this not 4 temperatures, but 4 million temperatures all over the world last year. Suppose you want to find the hottest spot in the world, okay? So then you want to make this lambda function. This is the main thing right here, okay? So this map function defines a little lambda right here. This is given an input called x. It's going to be a Celsius. Just basically approximately double it, right? So times 9/5 is doubling it, and add a 32 to become Fahrenheit. So what do you do this function on that whole array? So here's your data. You can do it in Colab, sure. Then you get Fahrenheit, and we're going to print it. Just 3 lines. I'll fix Glot afterwards. Okay. Then we just print Fahrenheit, okay? Print Fahrenheit. Okay. Print it. Run. Okay. Oh, no way. So now what can we do? There's a Oh yeah. So this is a very interesting question. How do you actually print this? Yeah, exactly. So do you actually need to say like list underscore here? What if you actually print this? See, I don't use Python, can you tell? There's some crazy way, that I never memorize, okay? If you actually put up the syntax, I'll print it. But if not, I'll do it in JavaScript. Oh, wow. Oh, I see. So you need to list it. Okay, thank you. Oh my God, that's the one that I forgot. Yeah. See, Python, makes you like do all this weird stuff. It used to work in the past without it, but I appreciate it. Okay, list one more time. Wrap it in a list. It's weird that, see, map needs to take a list as an input, right? And then supply a list as an output. But it doesn't. So you need an actual list constructor to make like a real list out of it. Wow. One extra hope, no big deal. Exactly, wrap it. Okay. Sorry. No. Oh, wait. One more time. Yeah. Finally. All right. So that's pretty much all right. So like that. Show that it's live. Oh my God, freezing. All right, this is all. But now what I'm going to tell you is this is big data. These are all Medium articles, like, a million Medium articles. And then this operation, this operation, as a matter of fact, is going to run on all of them in parallel. That is what I'm trying to simulate, okay? So right now, if I, do this, you know what I'm talking about. Right now, if I replicate this a lot of times, I'm just going to do a little comma like this and just keep going like that. So this is a trivial way to just replicate, right? It's growing like crazy. See, even that is going to take longer, unless I have like syntax error or something to run. See, that took a little, like a small little fraction. See, like that. Pause, run, pause, run. So you can see if I then make it 100 times, it's going to hang, right? That is exactly what you can do pretty fast. The iteration is done by, oh, somebody asked a question. Yeah, right. So that is, the Lambda function does not iterate, you guys, okay? Let's actually get this right. The Lambda function does not iterate at all. What is happening is the map function is doing the iteration, but the map needs what to iterate. The map says, what do you want me to iterate? And then the Lambda says, iterate me. Instead of Lambda, you don't need all this at all, by the way. I could have made a separate DEF function, okay? A function called DEF, Celsius to Fahrenheit, C to F. Then I can just name that function C to F right there. This is simply a function name, okay? That's all it is, okay? This is a function name. The function name can be an actual function, or it can be like inline. That's all Lambda is. So Lambda does not know how to iterate. The map knows how to iterate. Cool. All right. Wow, this took longer than I expected. All right. Let's do this in, no, we don't have time. All right, this, I'm just going to show it to you right here. JavaScript is pretty amazing. It's my favorite language. What it is it does this. You have a function called runMe, and runMe takes two pieces of data, A and B, right? Like this. But runMe takes a function. And so then it's going to call your function on the data. For example, here. Oh, come on, just do it. Okay. Well, we'll do something else. We'll actually do it here. Bear. So I have a weird UI here called bear. A function literal is a little bit different, but it's okay. Okay. So just grab this. You need a function and alert, okay? Rather than alert, I'll even show you PRTT. So I'm going to copy it. Go here. Copy it. Okay, so it's already working. But I don't want to run alert. Okay. And do PRTT. Sprint right here. All right, so yes, CG is correct. In a functional programming language, functions are first-class citizens because, see, this M is that function right here. This is an anonymous function. The point of all of that was XY is not named anywhere, okay? But function XY return XY can easily be pulled out. See, this little function can easily be pulled out, and then that can then be separate. See, like this, suppose you pull it out. Then, in fact, it's right there, right? I could name runMe right there. I could name some other function like, FFF. As long as that function is defined separately, it's going to work. All right. So you don't need it separately. You can define it right here. Is the point. Okay. So moving on. Filter. This is all still map operation. This one is to tell you anonymous functions in JavaScript. Filter is a lot like map, but one difference. In a map, what happens is every single input will turn into an output. Meaning, you give me 4 elements, I'll give you 4 elements back. Filter does what it says, which is it can filter out some of these elements, meaning you'll not get some output based on, in this case, whether these numbers are odd or even. For example, say these are all locations all over the world, then you can say, give me only the US locations. So that is called a filtering operation, okay? So just to show that it's a very similar, call. It also takes a function and some data, and then in parallel processing, we can parallel process them. Say you take a Fibonacci sequence, you know, say 0 plus 1 is 1, then 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, and so on. One question is going to come up pretty soon. Suppose you say, return me only the odd numbers. Then here's the filter function. There's your Fibonacci array, and then this is the call that you run. For every x, x mod 2. So even numbers mod 2 will be 0, correct? Odd numbers mod 2 would be 1, and 1 means yes. So in a filter function, the data should be paired with a Boolean function that is true or false, obviously. So when the Boolean is true for any element, that'll be output. If the Boolean is false, like for even numbers in our case, it'll not be output. So this is an easy way to filter out 0, 2, 8, 34. Okay. So say you want then now the opposite. Suppose you want the even numbers. Then you want to see if the number is even. Then you change your function, the lambda function a little bit to say, tell me if this is 0. So you need to explicitly compare the 0, and then you will get the complement. So this union, this is going to be that, right? So odd numbers, even numbers. Anyway, this filter, and the filter is not used in parallel programming, so you can forget this. But just for fun, I'm showing you filter. Very briefly, you know, because we don't have too much time. What will happen if you go on dividing, or what will happen if you go on doing this infinitely? What happens to all these numbers? Like 34 plus 55, 88, 88 plus 55, just keep going. The numbers get smaller and smaller, bigger and bigger. What happens? So in the limit, when you have infinity of these, how large does the number get? Yes, you can say bigger, sure. So that's a simple question. That's not my question really. What will happen if you divide any number, the last number, by the previous value? In this case, 55 over 34. And then 34 over 21, 21 over 13. Exactly, good. They're all not the same, right? But when these numbers get massively large, what will happen is that ratio, that right there, the ratio of the last, by the one before, it's an amazing number called the golden ratio. What is that equal to? 1 plus something divided by 2. 1 plus square root of 5, okay? So please look this up. 1 plus square root of 5 divided by 2. That number is called the golden ratio. It's a cool number, okay? The Greeks actually discovered that and used it for architecture. It's completely beside the point, but why the hell not? You can prove it analytically, okay? So write an equation, a recurrence relation, and please prove it. Oops, sorry, by over 2, not by 6, okay? Over 2. Okay, moving on. It's 1 point, I think like 1.6 something. Or 1.618, sorry, 1.618. Okay, so the MapReduce, let's actually then keep going on. So here's Python Fiddle. Let's see if this runs. Python Fiddle. Yeah, see, we should use Python Fiddle. So Python Fiddle is also a place where you can do online like Python stuff. Like here, right? I'll show it to you. You have Fibonacci sequence, and then the thing that I showed you, you know, you can run. I'm not going to do it, okay? I'm not going to go to plot again. Let's do reduce. That's more important. Okay, so reduce is a little bit magical, you know, you need to think about it, okay? So here, that reduction operation there's a base, like a starting problem, so to speak. This operation, automatically reduce, will apply to all the elements. So in this case, when you say reduce, just apply the x plus y operation. The initial number is basically like an invisible 0, okay? So it's going to do 0 plus 47. The first argument, the very first time is 0. So 0 plus 47 is 47. After that, to the result 47, the y would be 11. So the result is 47 plus 11. Plus after that, the next y is going to be 42. In other words, it'll systematically reduce all of these and become one value. This is supremely heavily used in big data programming, okay? Because you're counting so many things. Say I give you a full book, and I ask you in the book, tell me how many times the word the occurs, like the word the occurs. So what you would do is every time you see the word the, you go into an array like this and just say 1. You see the word the again, there's probably like some words, say 1 again. So I get arrays full of 1, 1, 1, 1, 1. That's all I get. Then it's somebody else's job to add it up. It's the reduce's job. So reduce can trivially add all the ones and say you have 400 ones. Oh, okay. So that is how that works, okay? Because I can take my book and cut the book up into 100 pieces and ask each of the 100 pieces, count how many, you know, those do you have? Then I'll have 100 different arrays, and they'll all have 1, 1, 1. And then at the shuffle stage, you can do something called combine and make them into one giant sequence of 1, 1, 1, and give it to a reducer like that. All right. So reduce just repeatedly calls that function, okay, with the current result. There's always a current result. And then in the end, unlike map, where if you have 4 numbers come out, reduce is more like a column operation in a table. You get just one value back, and that's what reduction means, okay? Like in a GPA example, suppose there are 4 different servers that give us 4 min GPAs. Then you say, what is the least of all of them? The answer should be 11. All right, so does the find feature control map reduce or something else? Yeah, that's a good one. Maybe not on PCs, but you could use MapReduce. So eventually, when things get quite large, Find can absolutely use MapReduce. Find uses more indexing, actually. They index it all. And so then it's a trivial form of doing it. But yeah, when your machine gets quite large and then you link your cloud to the Find function, then they have to do something like MapReduce. That's a good question. Search engines would absolutely work like that. Okay, you guys, so moving on, okay? Tell you I have like more. Oh my God. Okay, so today is not a lucky day. No Glock. Forget Glock. Or forget Malwarebytes. Okay, so of the triplet, I showed you what it is. The main thing that we need, by the way, here's another one. All right, so these are all elements you can cook and make food, right? But before you do that, filter, and this is the filter function. Please only pass the vegetarian items, please. That is me. So then you eat is the reduction. They all end up your tummy, and I'll leave it up to you. To look at the little poop emoji. So that is map, filter, reduce. Okay, it's pretty funny, right? On the other hand, if you just want map, reduce, that's the map reduce example. All right, now you understand map reduce. All I have to do is to show you how it actually works. It's a very powerful combination. And then it's all because you take big data and then you apply operations in parallel. And that's not a funny thing, it's a serious thing. I'm going to tell you a story, okay? eBay, LinkedIn, Yahoo, Google, all of the Bay Area, Silicon Valley internet companies had the same problem somewhere in the turn of the century, late 90s and early 2000s. The problem was the data that they started collecting from people grew bigger and bigger and bigger and bigger and bigger, and they just could not process it at all. In case of Google, there was a pretty simple little Google search, just like this, and then you type some word, and then when the index got bigger and bigger and bigger, you had to wait for many, many seconds, if not minutes, before it came back. So Google said, we're going to go out of business. No one's going to use a search engine. We're stuck because we have a large piece of data or index. How the hell are we going to search through it? They came up with MapReduce, and it's implemented right now. We almost got 10 billion results of data. Wow. That's probably one of the largest results ever, right? Tells you how popular data is. So they had to invent this algorithm from scratch. Okay, so those two people wrote the paper, and you see they thankfully published that paper, which is actually very cool. You can go read the paper afterwards. Here they talk about their idea, In fact, if I can bring the slides up really quickly, I'll show it to you. Arrow doesn't work. Okay. Well, in fact, look at the motivation first of all. See, like right there. This is crazy, right? Thousands. Now they have actually hundreds of thousands. The OR became off. Okay. Automatic parallelization, fault tolerance. Yeah, absolutely. Garima has a very, very good point. They absolutely did not invent parallel processing or distributed processing. They simply put it together on the internet. They said we can hook up servers with IP addresses. In fact, I answered that further. They came up with the parallel thing behind this called the Google file system, okay? They also published the paper separately. In fact, they published the file system paper first and then the MapReduce paper afterwards. The file system makes it so easy for people that work inside Google. If you work on YouTube, if you work on Google Docs, what, to program as if the whole file system, the entire Google file system exists on your local machine. You don't have to worry about exactly where these are. There's one called the name server, which knows the mapping to all of the actual, they're called master slave, okay? It's just the term that they use. So the master server knows all where they are. So you only write one mapper operation on your local machine and you simply trivially do it, okay? All of this done behind the scenes of people that work at Google. They made it as painless, as seamless as possible. And obviously they scale it up like crazy. There it is, right? So you simply specify a map function and then like a reduce function. Don't even need the list that's for output. Then combine this intermediate, this called combination. I'll tell you about combination. But the main thing is the whole map idea, okay? See, again, they tell you, like where this is all coming from, functional programming languages. Okay, then that's what map looks like, like that. For each word, every time you see the word, just simply emit a 1. That's what I told you. Then you're going to get an array full of 1s, okay? And then you add all the 1s by plus equal to. Initially, this is 0, and then 0 plus 1, and then plus 1 plus 1 plus 1, what? Then you get that. It's too easy. Okay. But then they did it, and it absolutely worked. Like, oh my God. And then, everybody started using it, and then it just completely took off, okay? Okay, so this again, what it is. You input, this now your database, your full 40,000 students. You break it up into chunks. And then you do things. Say you're looking for different things. Say you're looking for people's names, okay? You're also looking for their GPA. So name would be a key called name, and then GPA would be a key K2. What group by means you combine all the names together. See, you're looking for all the students whose names, the GPA more than 3.9. So here I get some names, get some names, get some names, get some names. So the name would be K1, name colon some student's name, comma some other student's name, some other student's name. Likewise, this next machine is also producing a bunch of names. I want to combine all the names, right? Because they're all names. That intermediate grouping is simply called grouping. Then it makes it easy for the reducer to just simply list all the people's names. Okay, so grouping is like a temporary combination based on keys. That is why these keys become so important in the mapping step. Okay. All right, so this is actually a good set of slides, but I have very similar pictures. I'm going to show it to you. This is the key right there. Key. All those steps are running in parallel. Not 3, but 300,000. Google won't even tell you how many servers they have all over the world for that to happen. 10 billion, you guys. That's more than the number of people in the world. Okay, so many pages have data in them. Holy crap. But that's MapReduce. It's pretty much unlimited parallelism. And you can reduce them. You can have more than one reducer, all running again in parallel. It depends on what the reduction step is. And then after reduce, maybe the data still needs to be mapped and reduced. So you can have stages of them. But then again, one last time, the big win is right there. You take your most difficult task and you parallelize it. And then you deal with like what happens afterwards. All right, so then story. Google came up with MapReduce. Then in the meanwhile, a small search company called Nuch also faced the same problem. So the Nuch programmers said, wow, we're going to go out of business. Yahoo said, we're going to go out of business. They all said, oh my God, we're screwed. What do we invent? This internet, help. So then the Nuch was going to close. Thankfully, Google people introduced the MapReduce paper and the GFS paper. The Nuch programmers jumped on it and said, holy crap, you saved our lives. Thank you. That is Hadoop. So Hadoop is simply the public implementation that you and I can run off the MapReduce algorithm. Technically, the word MapReduce belongs to Google. So you only can run real MapReduce only when you work inside Google, okay? Why not just tell you a tiny bit more? This is not good news. It's like weird news, but I'm gonna tell you. So this guy, if you Google his name, they'll never tell you all this is old history. Nobody knows that he invented MapReduce. The young kids don't know. But what they know is, starting like last December, and then still going on, some unsavory things have started happening at Google. Basically, it's all about bias in artificial intelligence, data and machine learning data. If your data is pretty heavily biased towards white people or towards male and against females, what, right? Then the machine learning is going to learn the patterns and then produce like bad results. So there was a woman, Timru, she actually was the head of the ethics, AI group. So Jeffrey sadly had to fire her, It was done in a very bad way, actually. She found out through like other people. And then her colleague called Melanie Mitchell. So now she also was basically fired. So her tweet on a Friday afternoon was, I'm fired. Wow. So these are very bad things, right? So I'm not going to take sides at all. I'm not going to tell you Melanie is right or, Google is right. Like Melanie Mitchell. Okay. I mean, there's a lot in here. Okay, you can go read it. All right, so then, that's all like not good at all. See that? No. All right. Margaret Mitchell, what did I say? Melanie Mitchell is different. See? Okay. She's the one who got fired. All right, so there's a lot of history with Jeffrey Dean. Unfortunately, he's in the news, in the limelight for like bad reasons. Okay. Meanwhile, though, he invented this, which is we're thankful for it. I'm going to tell you this. Step 0 is a pretty trivial step. You take your big data and you do horizontal fragmentation. And this is why no joins, because all the data you want should be in one place, and it is. It's easy to just take your documents and break them up, okay? And then each piece is now called a node, like partition. They're all going to run in parallel. And this is the function you want to run in parallel. So you write this function. You can write them in Java. You can write the function in Python. You can write it in JavaScript, Visual Basic, so many languages. Just simply find a way to write it. And then you copy that function. The MapReduce will automatically distribute it. It will put that function, a copy of the function, to run on all the nodes in parallel. All right. So then then they run in parallel. Each mapper in parallel produces output. But the output is always like a JSON kind of key value, because those keys can all be combined, I told you, okay? And that combination is all done in a step. In fact, it can be done in 2 different places. The mappers themselves can actually do some local combination. Maybe some keys can be combined with other keys. Then that's called the combine step. Okay, there's pictures for all these if you're wondering. Wait. So before I tell you all the pictures, I think I'll just verbally tell you, like I'm talking about all this. Like that's what I'm talking about. Meanwhile, let's tell you. So the mapper can do some combination, or if all else fails, the shuffler can definitely do the combination. The shuffler will do the combination based on similar keys, because it'll then take similar keys and send them to a reducer. It'll take a different similar keys and then send them to a reducer. A third set of similar keys, send them to the third reducer. So the keys are what makes reducers also go in parallel, okay? So the shuffler does it invisibly. All right. And then that's what I just told you. The shuffler sends all the keys and the combined values to multiple reducers all running in parallel also. Why not? So then for every key, you'll get a value. Just to make it more concrete, what do I mean by shufflers and multiple keys? Supposing the mapper's job is to take a book such as Alice in Wonderland, give you Alice in Wonderland.txt, and then I ask you, one student, find me every single occurrence of the word, the letter A. Like count all the A's in Alice in Wonderland. Count all the letter I in Alice in Wonderland. Count all the E, count all the O, count all the U. 5 vowels, right? So at the end, you'll give me 5 numbers, 1,000 A's and 200, use what. Okay, so then it's going to take you a long time to for you to do it. But if I tore the book up into 10 pieces and I gave to 10 students the same task, which is you take 1/10 of the book, you take 1/10, 1/10, 1/10. All of you count A, E, I, O, U. And each of you, when I come back to you, give me 5 numbers. Your A, E, I, O, U, your A, E, I, O, U, yours. So those A keys will all go to a shuffler, which will then say, I found A 1, 1, 1, 1. I also found A 1, 1, 1. All those A's would then have all the 1, 1s combined. So there's a single A with a whole bunch of 1s. That is going to be sent to an A reducer. The shuffler will take all the 5 different E 1s and make one long array with all the E 1s and send it to an E reducer that will reduce all the 1s. It makes sense, right? So that is the notion of the whole key part. So the key would be A, the key would be E, the key would be I, O, U. The keys are very important. Okay. So and then for each key, you will get a total. In the end, the 5 reducers do their work, and then you will have 5 totals, A, I, U. It'll be a lot faster than one student can do. If I have 100 students, then I break the book up into 100 parts. So you get the idea. I tear a page, and I give it to each student. Or I cut a page into 4 pieces and I give it to 4 students, okay? I mean, it's endless, really. One sentence, I can even give a student a word and say, within you, tell me how many A, I, U's. Maybe even 0. Like in this case, there's no A, there's no I, there's no O. Actually, there's only E and U. So the student would give me 1, 1, and then 0 for the rest. You get the idea. All right, so let's go. Okay, that's all it is. All right. So combiner, so therefore, if there was a combiner, I'd call it step 1.5. Okay, so step 0, data preparation. Step 1, run in parallel. And then step 2 is shuffling. Step 3 is combination. That's it. All right. So if you read, this makes a ton of sense. Like this. This is your big data. And then you horizontally fragment them. And then these are all mappers. So each is a mapper. And then each mapper is looking for 3 different keys, okay? So now there are 3 colored keys. So the mapper just blindly, all of them will just send everything to one shuffler. But the shuffler would collect all the keys, collect all the green keys. Maybe it's the letter A, or it's the word the. Maybe this is the letter off. This is the letter end. And then just send all the 1, 1, 1 coming from everywhere to all the ones that will just add all the ones, add all the ones, add all the ones, and give me 3 different totals. You don't need to do any of this at all. You could go back here and do it manually over and over and over. It'll be much slower, is the point. Same here, my big data comes in 4 different fragments, and I'm doing 4 mapping operations in parallel, and then they're all forwarding the keys. The shuffling is the green part. The shuffling combines the keys. It combined that key, that key, that key, okay? It's sent to that reducer, and it's getting, so 4 reducers. You can even reduce them one more time if you want. This is another example. Again, here the key values are just KV, right? Okay, so in this case, you have a little bit, more data in the sense you have A occurs 1 time, and then B occurs 2 times. Okay, that's what the mapper found. In other words, I gave it lots of data, and I ask all of them, find me how many A's, B's, and C's. This mapper did not get data that had C's in it, so it said A 1 time, B 2 times. Good enough. This one has found C, but it's finding C separately 3 times and separately 6 times. There can be 2 parallel processes. That's why the combination can happen right there. Why send a 3 and a 6 and the shuffler adds a 3 and a 6? You can add it yourself, okay? Because the keys are the same. So local key combination is called combined step. And combine it just to minimize the traffic, through the network. And then this third mapper found A and C. It did not find B's at all. When you combine them, nothing happens. You still get A and C. Nothing to combine. This one also nothing to combine. They found a B and a C. But now the idea is you want to combine all of those A's, B's, and C's. So this A1 and this A3 are sent to an A reducer. You're going to get A4. Again, based on keys, right? So the B key and then this B key. So 7 and 2 would get a 9. And then this C and then this C and then this C. So 9 plus 2 plus 8 is going to be 19. Instead of 9, you could have sent 3, 6, 2, 8. You're going to get the same 19. But then it's a little bit savings right there. So that is what happens again, okay? One more time. I hit you in the head with it so many times, you'll never forget this. Again, this is your big data, fragmented. By the way, a mapper does not have to only deal with one fragment. You can give a mapper more than one fragment. Mappers can even be different machines with different strengths. Some run fast, some run slow. The ones that run fast, you can give them more blocks, okay? You set all this up initially. Okay, so blocks 0 and 2 go here, and then 1 and 5 go here, and 3 and 4 go here. Cool. And then they're running in parallel. This is the big step. And each produces 2 keys. And then the shuffler just, shuffles it, combines the keys, really, the combination, the shuffler combination. And then reducer, 2 different outputs. Again, you don't need to do any of this. It'll take you longer to get from here to there. One more example. This is actually important to tell you. In the real world, a lot of times, only the value matters, okay? Like GPA, for example, might be the value. And maybe student ID is the key. Suppose you're looking for the lowest GPA in all of USC. We don't need to know who the student is, okay? It's probably embarrassing. You don't need to know who they are. I just want the value, okay? So you can put fake bogus keys. That's what this is. So in this case, we ignore the keys completely, even though they look a lot like the values. Because what you're actually counting is how many times the value occurs, okay? B occurs 1 time, C occurs 1 time. Every time I see something, I say that, comma 1. I repeat it. Like I saw D once, I saw D once again. I'm never going to say, oh, I think I saw D 2 times. Let's slow it down. I made a whole bunch of ones. The shuffler combines them. This one, that one, and that one got combined into 4, and reducer would add them and get 4. It's pretty elegant, right? They're all doing what they can very easily do. You don't need, like, why should this one add it up? Like, why not they all add it up? Because it'll slow them down. It's basically specialization. So everybody does what they do really, really fast. And then the combination is as fast as it ever gets. So MapReduce is a programming model and an implementation for processing large data sets. Users specify a map function and a reduce function, of course. Okay, reduce function. This is why in Couch and MongoDB, I showed you the API the other day. You can take your Couch data that has 1 million like medium blog posts and specify this map function and reduce function right there in the function call. Okay, in the database API, there's a place to supply a map function and a reduce function. And then the underlying engine would automatically know how many nodes the Couch is running on, and it can do the horizontal fragmentation. So you would never do anything. For you, magically, this will be faster than if you had never done it. Wow, right? Okay. So this is the file system that went along with it. And so Google wrote like a paper about it, which I can show you. The Google file system, GFS. This time I'll just show you the PDF, okay? Again, the details are not important. It's more like if you like operating system, you'll love it because it's exactly what it is. They took what existed before them, like the Unix, the network file system that Sun had. Sun had an amazing file system called NFS, okay? These are all based on Unix file systems. So then Google did the best of like all of them, but this is the main deal. They made a master that knows where all the different slaves are. And so that way, when the programmer inside Google writes something that searches through Google documents, you go to drive.google and you're looking to stuff, right? Then you're basically writing as if all the Google Docs existed in one master. But then that will then distribute the task automatically because it knows how many slaves are. The slaves are called chunk servers, okay? These are the ones where the mapping happens in parallel, but this is the one that receives the mapping code. You see, this mapping is kept in that machine. User doesn't care. User meaning Google programmers, inside Google, they just don't even know. Fully abstracted it. It's just beautiful. All right, so then this gets into what like all of this is what guarantees the file system provides. It's classic operating system stuff. It's clever. Okay. So like all those, okay? All those actual directory names, nobody cares. You think that it's all based on your /user/bin, It's like right there. Just write the code as if that's true. And then they do like all of these things. They can replicate many chunks and then fail recovery. So if one of those chunks fails, by the way, then the mapping task will automatically be distributed to a different machine that's probably finished. It's called load balancing. They can do it. All right, so there's so much built into GFS. No wonder things like Drive, YouTube, right? They all just work and work and work. Those things never fail. Okay. So then they did not patent any of this, and they published this paper, which is why Nutch took it, and then we have Hadoop. Cool. So all that was here. It abstracts all the file system access so that remote reads and writes feel just like local reads and writes. That's the magic right there for Google programmers. And then it's not NFS, it's not all the things before, because striping. So this is actually very cool. So you take your data, striping is done automatically. Striping meaning horizontal fragmentation. And then you store them on chunk servers. And then the master knows what those chunk servers are. So now I'm going to tell you where Hadoop came from. These are the programmers at Nuch, okay? So Nuch used to compete with Google, but nobody even knows about Nuch because they're much smaller. So like right there, okay. Yeah, meet Hadoop. So it's like 2020. Okay. So someday go read about all that. Go here. Okay, so what were we talking about here? Right. So Google published the paper, right? And then they published MapReduce. So then, by the way, Google has this amazing research page. They put everything up in one place, like a master database for everything. Wow. That's even more than what the name here, by the way. So it's all here, okay? So let's see, look at that. Wow, they're busy. All right, go read. And then you ask, like, what the hell is up with the name Hadoop? Because Doug's kid was, very young at the time. So he had a little stuffed animal, right? A stuffed toy. And they would take the little stuffed toy to bed every night and he'd say, where's my Hadoop? Hadoop. So then Doug said to himself, that's a cute name. Someday I'm going to name some massively cool product Hadoop. And the whole world is going to know what Hadoop is. And that's exactly what happened. Yeah, it's adorable. It's funny, like right there. It's actually true. There it is. Oh my God. Hadoop. Okay. Like right there. Okay. Okay. The project needs a good name. He had one up his sleeve. Yep. All that. And then there it is. His son was just 2 years old. Hadoop. Hadoop. Okay. There's Hadoop. I have a 3D printable version of Hadoop, by the way. So if you ask me, I'll send it to you. It's funny. Okay. So that's Hadoop. Now you know. So Hadoop is simply the name that we give to MapReduce, okay, that we can use. And it's in all kinds of, public clusters. If you get a free account on AWS, GCP, on even Azure. Yes, that's so funny you say that, okay? I don't know if it actually occurred to him. You should actually mail him and say, before somebody else does it, please, 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 please do one, okay? Should not go off script, but what the hell, okay? I will. You can go here. Cinema 4D, that's a 3D renderer. Booting up, and then we have a front-end UI for it, written in JavaScript, of course. What else? Look, it's 3D. Whoa, cool. A little eggplant with a chain. Like, what the hell is that? It's like Gulliver's Travels. Okay, this looks like Gulliver. It's a little Lilliput people. Okay, you can position this exactly how you want, and then say render. The backend Cinema 4D is going to render, and I have an image. I can save it to PNG, make an NFT out of it. We charge like 1 Ethereum, right? $1,800. Oh my God. But if there's something that is worth doing that on, an NFT on, it would be the original Hadoop. Don't even give it away, right? Take a picture of it. Like, what the hell? Okay. So then this one Hadoop is these days. It's an operating system. There it is right there. You can ingest data, the parallel data, in practically any format you can imagine, even plain text if you want, relational databases, right? Server log files, electronic data interchange in the old days, even before XML. Companies like Alibaba, how would they work with other, suppliers and partners? There was a crazy file format called EDI that is probably still used in the world. Machines communicate with other machines. It's a structured data format, okay? Or CSV, Excel files, or XML, anything at all. If you write a front-end driver for it, you can go in parallel, sit on all those nodes, okay? And then the main thing is they all operate in parallel. And then you reduce them and then do cool things with it in the world. And it is not used just by businesses anymore. You can use it for anything at all. Industry, science, anybody can do parallel processing. That's all. So then HDFS is the public version of GFS. They also wrote a paper. And the paper looks so similar to GFS, but then they call things a little bit differently, okay? But the exact same idea. Why would it be different? Because GFS works. Okay. And by the way, before I forget, so Hadoop, does not belong just to Nuch anymore. Thankfully, they gave it to the massively large Apache organization that made it completely open source. So you can get the source for this. Actually, you go there right now. And you can actually, that's not good. You can actually go see, how they do it, okay? I think it's called Hadoop. That's easy. Just go here. Just search for it. Yeah, just download it. Just download. You'll get the source and all kinds of binaries, like right there. Then you'll see how they wrote that, okay? All right. So high volume data flow, MapReduce, consumer results. It's just beautiful, okay? And then I guess what I was trying to say was the file, the naming, the nomenclature for the master slave, they use slightly different names, but I'll just show you the diagrams fast. Okay. So they call it name node and data node. Okay. So name node is the manager and data node is the ones that actually do all the work, and they operate in parallel. Just know the basics of what I'm trying to tell you. You don't need anything more. You'll probably never change all this. These things have been done in every public cloud in the world, so there's nothing better than this. There's many versions of these. You'll probably not be able to improve it. Although I shouldn't say that. You know, who am I to say? Maybe you'll improve it. All right. MapReduce examples. So the classic example is hello world, right? Which is, word count. So you give, again, Alice in Wonderland. But there's a different twist on it. So what we can say is you can look for specific words, or we can say every single separate occurrence of a word, all the unique, distinct words. Tell me how many of those there are. Like in my page right here, tell me how many times the word word count occurs. Maybe it occurs here, it occurs a second time, probably occurs like a third time here somewhere, okay? I don't know. And on, right? So you can count the third time, fourth time. You get the idea. So finally, you'll tell me every unique word, the frequency of that word. What is that called? Word frequency table. What is it called? In data science, there's a word that lists term frequency. There's a better word for it. What about count? I'm talking about word count, actually. Like, the word hello might occur 20 times and then followed by the word the occurs 18 times. It starts with the letter C, by the way, and then ends with the letter E. I'll start giving away hangman, okay? Anybody? No? Nope. There. Concordance is what it's called, okay? So concordance diagram. So they call it concordance diagram. I'll show you later on when we do data visualization, where you can plot them actually, word plots. So concordance diagram, word frequency. You can just go read about all this, okay? Yeah. So in the end, what it is you're basically counting, how many words and then basically sorting them by count. Anyway, I want to show you the Java code. So in the Java code, what happens is the whole Hadoop is implemented like a module. So you can then import the module with all of the classes like configuration path, like all of these are class names, right? So every mapper that you write is a subclass of the mapper class. Likewise, every reducer, must implement the reduce method because they all come with methods that you need to supply. They could have made them interfaces, but they're classes, it doesn't matter. Okay, so you do all of that and you write your little class, right? And then there's the name of the class, extends mapper. It's the main thing. So your name of your class, extends mapper. And then you do all of this. The reason is you need to implement the map function. That's the big one. And then every time you have a new word, write the word out and then straight one. Word one. So I'm going to get a whole bunch of, keys and values of this, okay? So every time I see a word, I just say the word followed by one. Let somebody else combine them. It's like a pretty lazy thing to do. What this actually means is, I'll go in this sentence, word count one, is one, the one, hello one, world one, off one, Hadoop one, count one, the one again. But then somebody would combine all the keys and say 1, 1. Okay, that's basically what we do. Reducer would then do the plus equal to, okay? Every time it sees a new key, it'll just combine all the values for it. So then it reduces it. All right, then you can actually write like a main function for it, right? Where you name like all of those, okay? Public static void main, and then you can just do it. So then you set, and then that is the class name, and that is the mapper. So this is how you name that. So you compile this separately, right? Then you have the mapper class, and then you also have the reducer class. Then you have to name like all of them. And then this is the cool part where you tell where the inputs are. Where are my fragments? Where should my output go? Compile this and just run it, right? Just simply run it. And then you run it on the command line like this. So Hadoop, that's the command. And then fs, actually not this, sorry. This way you run. That's the input, by the way. In the input, just simply say, tell me what is in file 01, file 02. I have 2 shards, okay? The first one has hello world by world. Hey, that sounds like suicide. Okay, sorry. And then this one has hello Hadoop, goodbye Hadoop. Oh, cool. And then here's how you run it. You say Hadoop, and then the jar file is wc. This all goes in wc.jar. In the jar file, you usually have to name what the main, the one that has the public static void main is. That's the word count. So then this is the input, and then followed by the output. Then you go and cat the output, and what do you see? That the word by occurred 1 time, the word hello occurred 2 times, the word world occurred 2 times, Hadoop 2 times. We got it. Cool, right? But this could be 200 million. Holy crap. Same idea, okay? But the best part is you don't need Java, because wait till I show you all the alternatives. They are pretty cool as well, but less code to write. Okay. So just more examples, okay? Wow, okay. And then, just answer some questions. Then the whole code, if you want, is here at the very end. And then you can run it. So you can run it on an example like that. You will actually see it. Okay, just to walk you through, because it's a tutorial, you can run it. Do it on the Java command line, okay? All right, what else? Right, what if you do it in Python? So Python is much less chatty, much less verbose. It doesn't talk too much, it's quiet. So you do it like here. Env Python import sys and very similar, okay? So strip all the lines and make them into individual words like that, like actually here. Strip the new line and the white space. And then make the split. Now you get a bunch of words, like an array of words. And then for each word in words, just iterate. Is what you do. Just the word followed by one. So I'm going to get every single word, split one, the one, line one into one, words one, word one, line split one, and then reduce it. So reducing could not be very similar. Just simply combine them, okay? Okay. So then, like right there, okay, just ignore this. Details, just go look it up. You can run this in Python if you like. And then what happens on top of it is this. These days you pretend that there's a whole ecosystem, meaning so many tools are written to bring in data from the outside world. And at the bottom of all this is, if you're inside Google, it's called MapReduce GFS. If you're outside Google, it is called Hadoop HDFS. So what are all these things that help you? This one is just simply for job coordination. So both of these work together. What this means is when you have multiple mappers and what if some of them fail, these are like job management, okay? These are the least that we talk about because they're not that important. They just simply make sure that the whole pipeline is working. But these are the ones that actually deal with the real data, all of them. Actually Ambari is also a lot like Woozy, meaning a cloud operator would actually do this, okay? These can all run on kube containers, and so maybe this like Kubernetes containers. So this would do the container, like provisioning and so on. So these three are the least important, you guys, sorry. But these all directly have to do with data. What does that mean? This one is all about server log data. Wow, I can actually get lots and lots of server logs and then analyze them in parallel. Scoop is like you scoop it up. I have SQL data, meaning I have relational tables. I can run SQL and read massive amounts of data warehouse, maybe relational tables, and then partition and fragment them. I can do my warehouse operations over here. I don't need like a separate warehouse. This is my warehouse. Or I can do machine learning. I can do a ton of data. And then on this data, I can do machine learning libraries. It's called Mahout. Or I can do statistics in the R programming language. I can run R code on all of these. These are all like modules you can imagine completely separate from each other. But they all operate on this file system in parallel. Say I'm trying to find variants, I can find individual variances and I can combine them. Pig is just amazing. I'm going to show you about Pig pretty soon. Pig takes a very different approach to all this. Pig says, after you map and reduce, it looks like a graph to me because they're all like nodes, individual leaves, right? All the leaves operating, then I combine to like a parent node, which is the reduce. Say the reduce operation goes to more map nodes. That looks like a graph of operations. I've used the term before. It's called data flow. So data flow graph is just simply nodes passing data from one node to another node. But except our nodes are mappers and reducers. So Pig then says to you, just describe the data flow to me. Like, don't worry about what is a mapper, what is a reducer. Tell me what the graph looks like. And the Pig compiler will then analyze the Pig code and automatically create Java mappers and Java reducers, compile them for you, and run your data through all those mappers and reducers and give you the result. So you no longer have to write actual mappers and reducers. You operate on a higher level language called Pig. Cool, right? It's a data flow programming language. Wow. Hive is a lot like Scoop. Scoop can read any relational data. Hive can specifically do like data warehouse stuff, meaning I can run, again, SQL commands to bring in like a lot of data, but I can do things like, cube and roll up all those commands I can do here. So it's specifically meant for that. HBase actually does column data, like column operations. I talked about HBase before. So you can do column operations on all this data. So all of these are directly data related, right? It's so cool. But there's even more than these, by the way. But I'm just going to keep going. So the same thing is, so Hive and Pig, this looks more like SQL, right? This looks like its own language. So you no longer are writing mappers and reducers by hand. You're writing a high level thing. They'll then get compiled to mappers and reducers because this only knows about mapping and reducing. The Hadoop command that I showed you before does not know Pig or anything else, okay? It only knows mapping and reducing. So in the end, it all has to run on that command line, so to speak. Like you have to ultimately be able to run this. So then it doesn't matter. HBase is for column operations, Hive is for data warehouse operations. Two different things you can do with relational data. Okay, so in fact, to answer your question, it's here. So Hive has been called better than SQL because it does SQL-like operations, but in parallel. Okay, and then so no need to create relational tables. Just simply take all your NoSQL data and turn them into MapReduce jobs. But do the same operation that you might do in a warehouse, which is zoom in and then roll up, just go up and down. Okay, so then it looks like SQL, but underneath there's no SQL engine. There's nothing, no tables, but you can scale it up like crazy. So then to the point, this was a lot of code, like so much, right? Java is very talkative. Wow, too many words, like my friend Laurent used to say. So you talk too much, too many words. And then Python is much simpler, fewer compared to Java. But Hive is 8 lines. This is all, okay? And those lines look like SQL. Wow. So if you do this on an actual Hadoop cluster, you will actually get word count. Wow, cool. So then who created Hive? Facebook did. Nice. So you go from 53 lines to 8 lines. Beautiful. Pig, also probably like 8 lines if you leave out the comments, right? But it has a very different, very elegant idea, which is all about data flow. So you describe your data operation in parallel, right? Just write these commands. And then automatically the compile. So this language, by the way, is called Pig Latin. Igpe Atenle. Pig Latin. Ooh, Pig Latin. That's why it's called Pig Latin. The language is called Pig. So you write Pig syntax, like words equal to for each input generate flatten. This all looks like functional programming chaining, right? That's exactly what it is. So you tokenize the line, then you run the flatten operation, take that result, do a generate operation, and then make that for each. Wow. So in just one line, you can do like crazy amounts of things. Like all of mapping can be done in one line, and then all of reducing can be done in like 2 lines. This is crazy, okay? This is shuffling. So map, shuffle, reduce. One line, one line, one line. There's nothing shorter than one line. A line is a line, okay? So this is like ultimately as small as it gets. It's pretty wild. That is Pig. I used to give out a Pig homework, believe it or not, okay? So a few years ago, I had a Pig homework. That was a lot of fun. Suppose you take Mary had a little lamb, put a little nursery rhyme. You want to count all the occurrences of Mary, snow, Mary, lamb, like all that, right? The word lamb is obviously in there 2 times. That's exactly what you're going to see, okay? But then that's what happens. So automatically, those mappers run in parallel, so they have all that word count. And then they do a reduction. Just simply count them. Wow. You can have more reducers if you like. It's a data flow language. So you describe just simply data flow, and then the flows can be combined. You can do flow operations. Different flows can be combined into one flow. That's a combination operation. A flow can be broken off into multiple flows. That's the operation of combination. You can do lots of things with flows, okay? They're called stream operations if you want to read up on it. So take stream operating data, languages from like many years ago in computer science, and then apply them here to these streams, data streams, and you can run in parallel. In the end, you have a DAG, a directed acyclic graph. It's like a graph of operations. It's called a graph acyclic because you cannot take a reduce operations result and for any reason go back and map it again. Then it'll become an infinite loop, okay? These things would only have to keep going in one direction. So it is called acyclic. Otherwise, it is a directed graph because you go from top to bottom in this case. Yahoo actually, contributed to Pig, which is also pretty cool. Pig is also an Apache, project, so you can go download Pig and look at the source if you like. All these Apache projects now. Uzi is the one that does simply job coordination. So this is about multiple MapReduces. I told you, you can have one MapReduce, take the result and go to another MapReduce. If you don't have things like Uzi, you have to manually start and stop them. Meaning after the first mapping and reducing is done, only then you kick off the second mapping. And then when that is done, you manually kick off the third mapping. These are all shell scripts, they're pretty boring. But this can automatically monitor the file system for you. And it knows when the first MR is done, then do MR part 2, then the MR part 3, and what. So then it just simply does it all. Therefore, that's called Uzi. There's nothing more to it than that. Musketeer, one more pretty clever idea. So what happens here is this paradigm, this idea of doing staged, mapping and reducing processing became so popular in the world that MapReduce now has a lot more similar implementations, almost like competition. Microsoft has their own. Microsoft has their own of everything, right? It's called Naiad. So Naiad is also MapReduce, but they never mention the word MapReduce anywhere. It's basically parallel parsing, right? They've done it. And then Spark, about which I'll say a few words in upcoming slides, it's not different, but it does not use, it uses more abstraction, okay? They use more abstraction with pipes and sinks and sources. It's not like raw mapping and reducing. So in a way, it's an error to have them as two different things because Spark has to run on a Hadoop cluster. But at a higher level, Spark looks different. Okay, so Spark has its own syntax is the point. It does not use mapping and reducing. So now we have a new problem in the world, which is if you actually want to run actual mapping and reducing, then the database that works with it, the syntax that you bring in relational data is called Hive. And the graph, suppose you want to bring in graph data from my previous lecture, then you have to use this thing called Giraffe because Giraffe talks to Hadoop. But in the meanwhile, suppose you like the world of Spark, you like Spark very much, then the same kind of relational data to bring into Spark, you would need to use a different language that is slightly but irritatingly different from Hive. So you cannot take Hive code and run here because it won't run. You have to run Spark SQL. Likewise, GraphX is just a little different from Giraffe, okay? So you're basically stuck in this little world right here. And Microsoft says, hey, we can do all this too, you know. So then they have their own thing called Lindy, which is basically a ripoff of Hive, but then they changed it a little bit differently. So it only runs on Naiad. Like, what the hell? Likewise, they have a GraphLink, okay, which is actually pretty cool. I've used this before. It's neat, but it's not Spark SQL. Sorry, it's not GraphX, not Giraffe. It drives you crazy. So, but what you would love to do is run Hive on Naiad backend if possible. I have free Naiad credits, right? Though why the hell can I not run Hive on it? Sorry, not possible. I would love to run Lindy, you know, some kind of Lindy SQL code on Hadoop, but currently not possible. So there's only one cool answer. You need to decouple the backend from the front end. It is possible if somebody writes a crazy driver that actually can read Hive code on Naiad. But then that's a never-ending operation because every time you have a new backend, somebody has to write drivers from all the front ends, right? Likewise, if you have a new front end, you have to write a driver for all the backend. So the classic joke in computer science is this. Anything in the world in computer science can be solved using one more level of indirection. So decouple them like this. Come up with a new format called Musketeer, which is an abstract graph definition format. It's also an Apache project. Then all you tell any front end, I've shown you more front ends, is please write a driver, a one-time driver, to translate your front end into Musketeer. Likewise, you write one driver for every backend that there is. Look at how many backends there are, probably more and more in the world, right? And now any front end can get translated and run on any backend. Wow, cool. If I have M front ends and N backends, how many of these drivers do I need? M front ends, N backends. It's fully connected, right? How many total combination? Exactly M times N, correct. Here, how many drivers do I need? Cool, good. So that is the radical change right there. Suppose this is 100, this is 100, right? 10,000, 200, crazy. But you know, more to the point, 10 and 10, okay? Suppose there are 10 front ends, 10 backends, they're right here. Rather than do 100 drivers, I just take 20 drivers. So cool, okay? So that is Musketeer for you. Yarn, you go a little faster on this, simple. Yarn is what we have in the world today, okay? MapReduce version 2. Yet another resource navigator. Like yet another compiler, right? Yak. So Yak is a Unix meme. It's an old meme. Yet another compiler. Likewise, Yarn is yet another resource navigator. Basically, it's Hadoop part 2. Because when Hadoop came along, it was pretty wonderful, but it said everything has to go through the file. And also, everything had to be done in little like pieces. You know, you need to start and stop them manually, individually. And there was no good automatic load balancing. If something failed, if one of the mappers failed, a separate Uzi had to go and look at that, then migrate the task to like a different mapper. But what if the whole job management migration was done automatically in the Hadoop itself? Then that is called MapReduce v2, okay? So in MapReduce v1, the older one, this is the master node, these are slave nodes, you know? But if something failed, a separate system had to go and do the load balancing. But what we have today, MapReduce version 2, the front end also, the main manager also functions as a resource manager. It actively tracks all the mappers. So therefore, it can automatically migrate jobs and so on. Just a better version of, you know, the previous MapReduce, okay? But not from any fundamental point of view, more from an operational point of view. That's really all. Okay, so not too much to really say there. And then again, going back to all the whole ecosystem, the world of, you know, actual program people in the world use. What can we use on like a big Hadoop cluster in the world? Again, think GCP, you know, AWS, Azure, or your own cluster. You can do practically all the things we named in the previous lecture. Mongo, Cassandra, HBase, Hive, all of these can run on this amazingly parallel operating system. And then some things that I did not name, okay, like Solr, search engines, okay, do search engine, Cumulo, Giraffe. Basically any type of NoSQL data can all be trivially parallelized as fragments and then be mapped and reduced. And this list is even more growing, by the way. So these days, needless to say, very quickly, clouds make a lot of money by providing you an unlimited cluster of nodes where mappers can run in parallel. And so then that is called an elastic computing cluster, ECC. That's why Amazon calls it EC2. Elastic because you can define a minimum and a maximum of those nodes. So if you say minimum 10, maximum 100, you don't need to keep track of how many nodes actually there are. Depending on how much your input fragments are, automatically the provision between 10 and 100, and you pay for it. And each of those nodes can do the mapping in parallel and then reduce combination. Therefore, your business can run with as little or as many nodes as you need. Likewise, a storage is called simple storage service, where you're going to store all those fragments, the HDFS. S3 is what Amazon calls it. So this is the computing part of the cloud. This is storage part of the cloud. So Amazon makes a ton of money. And then Google was the second to jump into it, Google Cloud Platform. Then Microsoft came in last, Azure. So now they're all pretty identical, basically. Okay, they all offer the same thing. Just pick a vendor. And you run all of those through your browser, believe it or not, okay? Just simply upload data. In GCP, you can get Drive data from your Google Drive. You can actually do all of this. So the pictures look very similar, okay? All right, so this is Google again, compute storage. These things are all higher level APIs that can basically do like all of this. In other words, you can manually do everything yourself, but they can do things like BigQuery, where they can automatically parallel process your query. Okay, so these are just high level. This is machine learning actually on top of all of that. But again, this is the main part. Okay, so they're called cloud services. You elastically can cloud the storage, and also you can elastically cloud increase the processing. And then they give you like 99.999. It's called 999 uptime. That way, if they actually go down below that thing that they promise, then they'll refund a lot of your money back. 99.999 guaranteed uptime, like that. This is what companies like Amazon promise the customers. Something like that, right? Yeah, 999. You can read about it. So this means hopefully, they'll never fail, because they put so much resources into making sure that your business does not go down when you pay them like crazy for it. It's called service level agreement, okay? SLA, you sign it, they sign it, and then it's done. Okay, it's all great for businesses. This means we never have to maintain any of this. And then Google has this massive platform, right? And then they challenge the world, they especially challenge scientists. What they ask is, they tell you, if you're a scientist and you have the world's largest problems, so the world is getting drier, right? Climate change, climate collapse, climate catastrophe. I don't say climate change, I call it climate catastrophe. It's a disaster. Fresh water, it's all being evaporated, never coming back, right? And so then people are going to have wars based on water. In the meanwhile, 75% of the earth is just like salt water. So how the hell do you do desalination? Oh, it's too expensive with the membrane, so too horrible. Well, we'll give you computing, and why don't you model it? That's what this is, okay? So you can actually do modeling, and then at least simulation wise, show that it might be possible or not possible. How much does it cost? What? Google calls it exascale computing. To give you unlimited computing power. You apply for grants, by the way, you write like a grant document. Then if they fund you, then you can go and do all these big things in the world. There are all this before COVID-19, by the way, so messenger RNA. You could actually probably use, Google Cloud to discover like certain drug combinations. Yeah, right. But, I don't want you to maybe, make it seem like it's a problem, right? I agree with you, right? Technically it's true. But that is true for like anything else in the world, right? So I would not basically highlight that. I'm not disagreeing with you, but yeah, you do it, so what, right? But once you do it, you'll have it. So you should keep that in mind. All right. So yeah, although I like what you said here, this is actually very cool. So now I see where you're going with this. What CJ is saying is actually something pretty smart, which is you can use maybe some semi-supervised learning to possibly migrate your data from your old, formats to the new format. You can teach it, you can do by example. But maybe in GCP, there's nothing, you manually do everything. So I'm sorry that I said what I said, I apologize, okay? Because if you just left it at that, I would say, wow, that sounds pretty critical. But if you follow up with this, I see what you're trying to say. Maybe Google should also try to automate it and help the users, right? But you still do it though. It's like a one-time migration, you just do it. Okay, cool. So these very large problems in the world. By the way, only a few handful of languages, relatively speaking, You have machine translation available. There are hundreds, if not thousands, of languages that are very small, that are only spoken, that are not even written down. So our machine learning has a long way to go. Those languages are disappearing because nobody speaks those languages anymore. Look at this. Wow. Okay. So CG said something else. Oh, I see. Okay. Well, I agree with you. And if this was an exam question, you get points. Sure. Compared to GCP, right? For sure. Good. Maybe, AWS leads the way, then they all follow. Okay. Good point. Maybe they should hire people, maybe like you, and just say, how do you help people? How do you automate it? In the meanwhile, Google tries to give you like all this compute space. Okay, guys. This is crazy. Okay, there's so much water, but only so much is drinkable. The whole world should say, why the hell not? It's too salty. You die of thirst. You need more water. Well, then purify it. What do you do with all the salt? Find a way to dispose it. Okay, that's what this is. This is actually very scary if you believe like all of this, right? Like, look at this, demand is 40% more. And in the meanwhile, the rivers are drying up. Supply goes down, demand goes more. Classic disaster. Okay. Solve it, you guys solve it. So, like CG is saying right there, there's so much of shell scripts that are involved. And then you thought the documentation for, Postgres was all old and like all over the place. You had to Stack Overflow, Google it. These things are even worse in a way. Only if you're very determined, you can set up your own elastic MapReduce using nothing but a command line, like a browser cloud shell, by following all kinds of crazy tutorials. Okay, my job right now is to not show you even one tutorial, but to tell you it exists. If you read all of this, I'll just show you. I'll just say EMR in Amazon setup, Amazon shell setup. You'll actually see at least a picture of what I mean. It's very painful. You write shell scripts and you run them. And they change the flags all the time, okay? Meaning they change some configuration variable. And then if you then have an older version of the shell script, I'm talking about stuff like that. You change one flag somewhere, maybe that flag is changed. Your shell script won't run anymore. So only the most determined people can actually like run all this, okay? But it is possible. So then you can succeed. Like I don't know what that is. Okay. So then basically my point is that you can do it, but then you would rather let them do it. The pre-configured one's always available. I'll show you the GCP version of it. If somebody is very determined, oops, we don't want that, to learn all this themselves, then you have a chance. It's an opportunity. But otherwise, it's actually a pain. All right, so they all give you like, some cloud credits and you can just go do it all. But in the end, you see, you can run like all those things, okay? But then Hadoop, Yarn is what is being offered. There's Uzi right there. And I'm going to tell you about the Zookeeper. I talked about this. And then Kafka I'll mention very soon. Spark I'll mention very soon. Let's keep going. Okay, so again, what is the bottom line? All of this is now on the cloud. So no need to set up your own cluster really. But you can set up your own cluster if you want by doing this wonderful thing called a virtual machine. And purely for fun, you should do it. Suppose you already have a virtual machine running on your machine. Two main suppliers, VirtualBox from Oracle and VMware. So you have those. Then you can download free add-ons, which are called appliances, that load into a virtual machine and run on the virtual file system, that pretend that the virtual file system can be broken up into many fragments, and you can try and operate on all those fragments in parallel, meaning you can do a little mini Hadoop within like a virtual machine. Even though your real machine has only 8 cores, 16 cores, okay, you're not going to get infinitely faster. But you can learn all of how Hadoop works by having 100 fragments of text files and then running it 100 ways, double quotes parallel, and then doing the reduction operation. That's what I'm going to show you. All right, so it's like this, right? You can implement them. They've implemented them in VMs and you just run them. So what can you get? Each one of them comes in 2 different flavors, for VirtualBox or for VMware. Hortonworks is one of those companies that give you a Hadoop sandbox. If these links are broken, you can always find them. Okay, they move them around. Okay, see like right there, just download. So simple, just download it. And you get like a pretty large 8 gig file. Then you load the file into your VM, and then you go into your VM and you start doing actual operations. A few years ago, I had like a homework that had students do exactly that, and it totally works. You would not do it for real because it's not any faster than a cloud or anything, right? But the idea is that you learn how it all works. And the sandboxes are fun to collect. They're just free, right? Just get it. That's one. With these guys, you can actually get a certification. You can do a course that they offer, and then you can be Hortonworks Hadoop certified. then maybe it matters to somebody. You might get a job from somebody just because you have the certification. Mapper is an R programming language company. It's an old data analysis company. They also have a sandbox called Mapper Sandbox. Once again, just get it. When you say choose, those are your two classic choices, okay? See, VirtualBox, which is owned now by Oracle, or VMware, just get it. And then it'll run inside there. Then you can do all these really cool things, okay? So drill is also like a way to bring in like relational data, I believe, Apache Drill. And then you can run R code on it. Just do all the tutorial, then you'll know exactly what I'm talking about. If it's actually here easily, I'll show it to you. They all look like SQL, things that you run. It's not. If it's not a video, we can look at it. Okay. So then there it is. So installing drill. Drill is a separate download, okay? Install and stop it. There's a JSON file immediately. So that is the cool part that you do, okay? So then just simply convert it. It looks so much like, the standard SQL that you run. And so, but it's a, drill operation. And then you can do parallel processing. Assuming all this data was distributed on like, multiple nodes in your cluster. If you had real nodes, real different nodes in the cluster, it will run faster, otherwise same speed. But you're still getting the benefit of trying it out. So try out two of those. And then Oracle has their own virtual machine called Big Data Lite. And so then you can download that as well and then do Hadoop on this. Look at how many places you can do Hadoop on. It's like so cool, like so popular, like all this. And then you would probably like run that, okay, to load data into it. So again, just it's yours for the asking. What can I say? Try it all, try it all, try it all. And then I think this and this are the same now, so I'm not sure. Yeah, it is, okay? So the Cloudera actually merged with the Hortonworks, so I want to go there. IBM has their own called Big Insights. They, okay, just get it? They're one of the companies that moves links like so often. Oh my God, okay, but thankfully it is actually in here. So just get that, okay? Okay, it's a Big Insights, but same idea. They give you like a virtual Hadoop cluster inside a virtual machine. And then last but not least, actually two more, called the Talend. So Talend also has like a big data sandbox. And they can download it from the link that I'm giving you. So like 6 different sandboxes, right? Cool. So take the same data and then run them on all of them. That way you can cross compare them. Then you can put them on your resume. All right. That's not good. Which is why I think I give you this. Just Google it. Yeah, Talend free trial. All right, so in the end, you're getting like a sandbox, okay? And in which you can run these kinds of cool operations, and those nodes would get parallelized. So anything that can run in parallel. For example, these can run in parallel. And then those results, and then that result can be run in parallel. And then after that's generated, then those can run in parallel. I guess that's done, but this can run one more time. So you can automatically analyze what can be mappers and what can be reducers, okay? Okay. So and then finally Blaze VM. So these are all like batch based, meaning they read files off of your file system. But this one is actually real-time streaming data that you can get from a weather station or from Twitter even. Every few seconds, just find out what the trending keyword is, and just load that into the SQL Stream Blaze VM appliance. It's so neat. So it means you're doing parallel processing on incoming streams on your Hadoop cluster. So if you have massive amount of data coming in, then you can analyze them in real time. So real-time stream processing, okay, that's what this is. Wow. Streaming analytics. Software that provides analytical operators, again, things like mapping and reducing, to orchestrate data flow. That's your graph right there. Calculate. In the end, you're calculating numbers, like what are the top 3 trending words every hour. So then detect patterns, even data stock price. And then disparate live data sources. So many sources of data, maybe blogs, maybe tweet, maybe, Facebook likes, it doesn't matter. You can actually build applications that can get all the data from so many sources and in real time do all of this real time. So you can get data from sensors, classic relational databases, applications meaning scientific instruments like a telescope or a microscope even, and then actually people like driving and taking polls and surveys and what. Anything at all. Continuous analysis, streaming queries. Wow. That's why it's called SQL Stream. But there's SQL right there. Beautiful. And then this is actually very neat. VMware's CTO talked about virtualizing using Hadoop. What? Like right there. Like how did from the virtual machine standpoint, how did they make the Hadoop cluster be implemented so that we can then run our appliances in it? Okay, a little post about that. It's very neat when the CTO actually makes a post. You can read it. Okay, So moving on further, what is beyond MapReduce? Okay, there are many things that are so-called beyond MapReduce. The first of them, the most common, the most popular, is called Spark. Again, just to interest you, I can show you things like this. I can just say Spark Hadoop. That Spark job, Spark knowledge actually is in great demand. Okay, just instantly you start to see all these things. Big data, Hadoop Spark 25 more jobs, employment, indeed. Okay, there's a lot because people actually love Spark because Spark does streaming analysis as well. I'll tell you about Spark in a minute. Spark versus MapReduce. Again, this is streaming, this is non-streaming. Okay, but I have things in the slides. All right, so it first started at AMP Lab at Cal, 2009, and then they open sourced it. So again, real-time interactive, these are the two keywords. So no more ETL. You don't wait like a week or even the middle of the night and then load data in batches. It is constantly, basically like almost nonstop coming in, and then you can interact with it while the data is coming in. So then an in-memory data processing, this is the secret behind Spark. Why is Spark so fast? Because Spark actually has Spark objects that are called RDDs, which I'll tell you pretty soon. So the RDD objects live in main memory, and main memory is faster than disk. And so then they do all the operations in main memory. And then they combine those operations just to do that part. But the mapping is actually done in parallel on fast hardware. So you can iterate. It's an alternative because it's a little bit different, the RDD part of it. And then you can do general data flow. Again, from now on, I'll just use the word data flow. It is a combination of mapping and reducing. An execution graph is a data flow. So you describe the graph, and the graph will find a way to run in main memory. And then all these top companies in the world use it. And then the language to query is called Spark SQL. The Spark SQL came from a language called Shark. And then Shark was written early on as an alternative to Hive. These are all Apache projects. Okay, so Shark, and then afterwards Spark SQL. Multi-pass processing. Again, you do one MapReduce, do one more stage, third stage, fourth stage. You can do many stages, and then you can do interactive processing, and then Spark has like all of those. So in Spark, basically, there's a compiler that they call a driver. So driver would take your graph query, like just a general graph operation, and then convert them to basically mappers and reducers, which are called executors. They run in parallel. Again, the key is over and over. Something underneath can make it all run in parallel. Okay, this is the memory objects. I told you all the data actually shows up, your horizontal fragments show up in your main memory. Those objects, those data sets are called RDDs, resilient distributed data sets. So resilient because if they fail on one node, they can be migrated to another node trivially, okay? The resilient data. But the main thing is the distributed data, the horizontal fragments. Distributed collections of objects, meaning your documents or key value pairs, what. They can be cached in main memory across a cluster. I told you all this. And then parallel operators, like for example, the word map is a parallel operator. And then, so this is why it's resilient, because it is recomputed in failure. Okay, so one easy example, just visually, there's some Python to go with it, is like this. This again, this goes into our good old data mining, machine learning. Suppose you have, these are the Democrats across the aisle, and these are the Republicans. Fight. In between is an aisle, right? So sadly, the distance between them is maximized. You want to draw this line that separates the blues from the reds. Okay, people that are rich, people that are poor, people that don't want to vote for abortion control, people that don't want that abortion control, anything, right? You want to draw that line, that maximal line of separation. There's an algorithm for that, like SVM, scalable support vector machines. Suppose you want that line. You can get the line with an iteration, meaning you make an initial guess and you say, I think that's my initial line. But the line is so bad because a good line will have all of the reds on one side, all the blues on the other side, right? But then that line does not have that at all. That initial line slices through reds and blues. Then you can make this to be the next guess, the next iteration, next iteration, next iteration, next iteration, next iteration. You're changing the slope in every single iteration, okay? Basically like machine learning. These are the weights, initially all random weights. And then every time you do back propagation, the weights are changing, Now you have the most ideal at the bottom of the parabola. If you change the slope or the weight one more time, it is getting worse. You stop right there. That's an iteration cycle, almost like a back propagation cycle. You can do that in Spark just like that because it can iterate. Wow, cool. That's called logistic regression thing that I showed you. Is right here, okay? So take your data, meaning this is big data. Suppose this is x comma y, something like that, right? or sorry, I said that. XY, 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 XY. Each XY is a point. They're all separate points. But say you have billions of them, and you still want to draw this line. That is all in this big text file. But now I can break all of that into individual chunks. I can do local versions of these and then combine them all. That's what's happening here, okay? So that's why the map and then the read point. So you can do several clusters of them. And then here you do the actual iteration. Well, right there, you're actually changing the slope right there. You can reduce. So ignore 100% about how this works, but then it's basically what I told you. You're iterating. There's probably a different way to do it. You can just do a simple like a variance calculation, but this one uses iteration because the point is to show that you can go very fast. So how does that compare with like standard MapReduce? Like this. So this is standard Hadoop, okay, with the mapping and reducing. If you have more iterations, so the more iterations you have, right, hopefully, the better you'll finally get to the result. It takes more and more running time, so every time you pile on more iterations, you're just adding time. But the cool thing about Spark is, look at this. This is the first iteration, takes time to set up, but after that, every time you spin, it's taking just a tiny little amount of extra time. Wow. So overall, when you're done, this is what it took for Hadoop to, get to that line. And then this is all it took Spark to get to that same line. Wow. So then you can do it in Python, you can do it in Java, same idea, okay? Okay. And then, so this part, the main idea in Spark is, again, data becomes RDDs, and RDDs run on main memory. Now they have add-on plugins. Suppose you're trying to do streaming data. Suppose all this data was not streaming data, then you wouldn't need what I'm going to show you. But if the data was streaming data, which is here, then you get this library. Then you install Spark Streaming module. If you want to run SQL queries, actual SQL, then you install Spark SQL. If you want to do graph database processing, and only if, then you do the GraphX module. And finally, if you want to do machine learning, again, say this is actually backpropagation, doing weight training, then you would need the MLib, okay? So they all have different capabilities. You can read about them. But you can get only the one that you want. So then word count again, say you do it in Python versus Java. So then in Java, you have to do like all of that. This is like, again, Spark, okay? And then, so Spark word count in PySpark, so simple. That's all you do, okay? This looks so much like the Hadoop map function, right? Which actually it is. But the difference is that Spark will take all the data, make them into RDDs, and run them in main memory for you. Otherwise, the underlying idea is actually pretty similar. So I talked about Spark. There's one more called Flink. Flink is a lot like the good old MapReduce. But Flink is MapReduce plus. In the sense, in MapReduce, if I ask you, what are the two functional programming constructs? Well, it's map and reduce, obviously. In Flink, you have map and reduce, but you have more things like join. Join is when you have one mapper that produces like a bunch of keys, and a separate mapper that also produces a bunch of keys. You can combine them using a join operator. It is not just merely shuffling. You can do more. It depends on what join actually does. There's a join function you can write. So you can do more graph processing operation. That's what all this is. You can even do filter, by the way. So filter could not be done in MapReduce, but now you can actually filter some other data out. Or you can do iteration. You can actually do a for loop. The one that I told you is not possible. You cannot do a loop, right? Because loops are bad. Directed acyclic graph. But now you actually can have cycles in Flink. Wow. You can maybe have an upper limit for how many cycles, okay? You can do cycle n number of times. Then you can do like matrix multiplication, matrix iteration, right? Inverse, actually, stuff like that. Beautiful. So therefore, you can do graph operations. You can combine from many sources. And then you can sinks are the opposite of a source. Sinks means where the data ends up. I can have lots of different sinks. And then branching and merging. I should not keep writing in air, okay? I should actually at least do a little bit of like what I'm showing you. This time we can do like a whiteboard. What should I use? Let's use this one. Okay. We'll try and clean it out. Okay. Okay, never mind. Just do it on top. Okay, so what I'm showing you is this. You have a node, another node. These two nodes can be officially joined using a join operation. And then say there was a node here as well, and those can be joined using a join operation. Those join operations can be merged further using a separate kind of join. And that join can be split off into two different streams. And then that can go and join with somebody else. And then this can go and join with like this. Just trying to send to somebody. Okay, suppose this needs like one more from here. And then those operations can be joined. And then they can be split off. So you can do lots of joining and merging, okay? That's what can be done here. And then some filtering even. Say in between, maybe before you go from here to here, we run like a filter operation, and then send only some of this data like to over here. You can do lots of very neat things that you could not do in classic MapReduce. So Flink is again quite popular with people that actually want to do cool graph things. So therefore, it is more generic in the sense, you can do, by the way, you can also do at the data structure level, not just key value pairs, but also you can do a Java dictionary, or you can do a Java hash map, or a set, what. You can do extra things. And Scala is also a Java-like language, right? So you can do Scala programming. All those could not be done in good old MapReduce because all this is running usually on a JVM, okay? So Flink's native mode is like some kind of JVM that's running in every single mapper, every single node rather. Okay, then you have keys. So there are more flexible ways to define keys. Maybe the key itself can be not just a string anymore. Key can be a number or a list even. There could be all kinds of uses for those kinds of keys. Therefore, it's simply a superset of MapReduce because MapReduce only has map and reduce, but then we have a lot more and also a lot more like over here. All right, so then I can do like all of that. And then, yeah, you can just take unmodified mappers from like 10 years ago. It can simply run on Flink. It's pretty simple. One more. So I talked about Spark and then Flink and then now Storm. Storm is also incredibly popular. Storm and Spark are actually almost identical in terms of what they do, but the architecture is different. Because again, remember in Spark, the RDD is the main thing, the main memory running. This one, it does not run in main memory. But in Storm, streaming is actually pretty simple. You can do unbounded streams of data, real-time processing, and then Storm is simple. Real-time analytics, one more time. So Jeff Bezos, puts his feet up on the chair. How many millions of dollars I'm making every minute? Just literally watches, net worth go up. Online machine learning, that's very cool. Every time you click on a like, so Facebook can do machine learning, can add that to the training data. It's crazy that you can do that. Continuous computation, again, still seeing the same thing. Distributed remote procedure calls, again, you're running on many machines. ETL, again, live ETL. There's no like batch ETL. So Storm is fast. All this, okay. Complementing Storm. So Storm is used along with this very interesting thing called Kafka. Kafka is not directly about data at all. Kafka is more about what you might call a message. The message will have data for sure, like a tweet, for example, is data. But then it does not start out by saying, well, I have a piece of data. It's more like a message. So Kafka is, again, what is called a pub subsystem. I'll actually show it here. This is what Kafka is. You set up a whole bunch of what are called publishers. They're sources of data. Again, going back to question 4 in the midterm, they could be relational databases. They can be API calls. They can be CGI scripts. They can be instruments. They can be what, anything at all. An API call to a different machine over here. They're all sources of data. You call them publishers because they publish data. Inside, you have a list of them. You also have separately a list of other clients that actually want to operate on all the data. You call them consumers, okay? Then you have a separate list of consumers. But now you can chain them together. Certain consumers can subscribe to certain publishers. And then Kafka maintains a list of, who they are, what clients, like what consumers want, what producers. And then you will actually send it to them, okay? Okay, so like this, get it? I'll use that, okay. Want that, okay. So say, oh, that, I'll use everything today, wait, still, okay, good. Okay, so say these are all data producers, okay, 4 different producers. You got a list of them inside Kafka, list of them. Sorry. Say these are consumers. This consumer can say, I want that producer. So you maintain a list between them, okay? And this consumer can say, I want that producer and that producer. Then you maintain a list right there. So there's a list that is being maintained between consumers and producers. Then what happens is when the producer produces a message, the data is called a message, then that relevant consumer is alerted. You forward the message to the consumer. Just say, here, there's a message for you. It is simply a forwarding system, but it is loosely coupled because, again, it's a lot like Musketeer, where you don't directly connect this to this. That's pretty easy to do, but it's also very easily breakable because if this breaks, then that's going to point to a null pointer. So instead, you want a level of indirection. So it's right here. All the consumers are all like over, all the producers are all over here. All the consumers are like over here. And then you can wire like a table. This consumer wants that producer. This consumer wants that producer. This producer is wanted by that consumer right there. And then those things will be done live while data is coming and going, okay? This way, if somebody stops producing data, then you just cut out this link, and then that does not get the data anymore. The thing will actually break. So publish, subscribe. These are publishers, these are subscribers. Pub sub, okay? So pub sub system. Inside, if you want to know a little bit more, what happens is every single category of things that come in, they're called a message, like a Twitter message, Facebook like message, a Medium blog post message, messages. Messages are also called channels, okay, like a Slack channel, they're all different channels. Then a consumer can subscribe to a whole bunch of channels. And channels internally have what are called partitions. These are disk things. So when channel data come in, it is being striped. Say the Twitter channel. So some tweets go here, some go here, some go here. That way they're filling up the disk evenly. And within each partition, there are things called records, okay? A record is like a little piece of a partition, like first Twitter message, second message, third message, fourth message. So when a message comes in, the client will be told what partition, and then what is this offset, meaning it's almost like I have 0 here. The first tweet took up 100 bytes. The second tweet took up 30 bytes. So now 100 plus 30 is 130. The third tweet starts at 130 and it ends at 160. So everybody has an offset for where the tweet starts. That is all forwarded to the consumer. The consumer can very easily apply the offset, get the message, do whatever they want with it. So that is internally how it works, like with partitions and record offsets. They're called records. Each little piece is called a record. So again, message is the main thing. So everything is ultimately a message. And message goes into different partitions. And each partition has a bunch of records. And each record has a record offset. The first offset is 0, of course. And then the offsets are non-zero after that. All right. So now you combine such a forwarding system with the Storm graph. So Storm is a lot like Spark. We have a graph of data flow operations. So initially, Kafka is the one that is getting data from the world. There's so many world data. And then this just means different parts of the graph want this. So then different parts of the graph are getting different data that Kafka is forwarding to you. Then if you look at what a topology is, that is simply a graph. It looks like this. You zoom in to get a graph. Incoming data goes into inputs, Storm inputs. They're called spouts. So Storm calls a spout anything that is incoming. So therefore, that is going to be called a Kafka spout because you're getting incoming data. Anything that is not input is called a filter. Meaning, in Storm, there's 3 kinds of nodes: input nodes, processing nodes, output nodes. Input nodes are always called spouts. The middle nodes that are neither input nor output, they're called bolts. Unfortunately, the output also they're calling a bolt. I wish they had not called it that. I wish they had called it something else. Then you'll have 3 different things, right? There are 3 different things conceptually. The incoming nodes, the processing nodes, the output nodes. But the incoming nodes are always called spout nodes. This is part of data. And then the processing and outgoing, they're together they're both called bolt nodes, okay? That's all it is. Okay, so then you have a bolt going out, meaning you send some data out. And maybe the other topology is doing something very similar. And then Kafka treats all of those as incoming messages and forwards them to even more different graphs. So it's basically a way of taking one super graph, breaking it up into multiple graphs, and inserting pub sub in between. So it's a graph of graphs, right? Wow. That's ultimately what it is. It's a graph of graphs. Extremely cool. Okay, so then that is what I've said here. So Kafka is pub sub, and then Kafka nodes are brokers. So then these are called a broker node, meaning a pub sub system. One pub sub instance that would be called a broker. So then broker's job is, is to mediate between the publishers and consumers. Publishers are also called producers. Consumers are called subscribers. I use many different words, okay, but they are the same idea. One of them produces, the other one wants it. And then Storm does stream processing on all of them. So these things can all happen in real time. Imagine Amazon's businesses, their Prime, their music, and then the movies that people watch, and the vehicles that people rent, on and on, right? So many things that Amazon does. They can all be analyzed in parallel and go up in like different dashboards. Wow, in real time. The Storm is super powerful. And then they're all tuple. They're just like lists of data. Okay, so streams initially, where does a Storm stay? A stream just means streaming data. So where does it start? Obviously, it starts at the spouts. And spouts in turn come from live data. And then what do spouts do? That they send their data on to bolts, which are the filters. And then when filters finish, the results are also called bolts, sadly. And then they're the output streams. and then they become input streams for the next topology. This just keeps going. Easy. SAMZA. So SAMZA is also a fourth system. So they all start with the letter S. Have you noticed? You got Storm, you got Flink, you got Spark, and now you have SAMZA. SAMZA was specifically written just for LinkedIn resumes for you guys. Wow. Because when people started paying LinkedIn money, LinkedIn was a very interesting company, right? Initially, they told all the job seekers, this is a place for your resumes to, just like hang out and people can make connections with each other. So then millions of people joined, obviously. Then they went to all the people that want your resumes, like the Microsofts and Facebooks, the mafias of the world, and said, if you pay us lots of money every month, we'll give you unlimited access to all these students' resumes, and you can make direct calls, like just message them. That is what this is about, okay? So they wanted a pretty cool interface for some Facebook searcher to go and search through thousands of resumes. That's exactly what this is. Okay. So then you have like all the usual things, you got Yarn underneath this MapReduce, okay? That's the whole point of all of this. So then they call them like this an in-memory database, okay? And then you can do what looks like SQL queries. Obviously, the job search person, the coordinator, the hiring manager is not writing SQL. They have a UI for it. But whatever they're searching for, they put in keywords, right? And they say, find, and they find you. That is becoming a SQL query, actually. And the SQL query is running on all this. That's ultimately how it works. So they have a Kafka underneath, okay? Okay, so then they're on Amazon Kinesis. It's pretty interesting that they store like tons of things on Amazon. And then, but look, all that is actually backed by like a Hadoop file system. And they can use traditional data as well, meaning standard relational databases. Okay, but then the main thing about SAMZA is at the SAMZA level, it does not know if certain data is batch data coming from an actual file system, or even like an actual relational database, or if the data is coming in real time from a stream. It is unified handling. This is what makes SAMZA distinct from everything else, okay? Indirectly, they're all some kind of pseudo stream is what it is. Okay, so like this. So the client is sending like all this data, and all the data, again, just like in Kafka, they end up in partitions, is what I told you earlier. So partitions are what are called messages. So each little piece is ultimately one piece of data. But now you can search through all of them in parallel, because it's basically what SAMZA does. Because when all the partition data, meaning all those records, I call them records, are all combined and sent them into SAMZA processing, and you call it a task. The task does not know which one of those came from databases, which one of those came from streaming, what. It is all just some kind of pseudo streaming, okay? It's all called a task, okay? So that way it made the programming really easy internally for LinkedIn. You call everything a streaming task. Whoa, okay. So then they all go into partitions and then they become tasks, all right? And then you run some kind of high-level SQL on it. SAMZA SQL, look at that. Okay, this was so cool. Insert into Kafka product managers, select name, school from user profiles for a company to LinkedIn, and title of product managers. So they're basically rating themselves, okay? And this is a fake query. At LinkedIn, who are the product managers? Wow. They can mine all the product managers and make a new table called product managers. And then that can be consumed by somebody else, okay? But this is when they can actually, go into your school and say, select name, school from a list of student resumes where GPA equal to 3.9 and, major equal to computer science. Wow. All the 3.9 CS students with their names and schools will end up somewhere. Crazy, right? Okay. So that is what SAMZA SQL is all about. And then the user-defined functions is like spatial databases, but they can write a UDF that is basically a resume. So each resume is like an object, okay? So UDF, then you can operate on resume's data. Like when did the student graduate, what's the GPA, what, I don't know, front-end experience do they have? So if you do a SEO, meaning if you carefully list your keywords in very specific ways in your resume, then that'll actually help the LinkedIn backend. Cool. Okay, so that's SAMZA, okay? There's 4 different things, like what the hell? There's Spark and Storm and Flink and SAMZA. Stop it. They all seem identical, but there are differences, okay? For example, Spark, Flink, SAMZA. They can all handle batch and also streaming. In SAMZA, there's no difference at all, but obviously it means they can handle it. And then Storm is, specifically for stream processing. So then this is the summary in a way. If you want just purely batch, you have no stream at all in your whole world. You're doing archaeology. What can possibly stream in archaeology, right? Every few hundred years, somebody digs up like a new pyramid or something. So it's no big deal, right? New mummy. That can all be batch files, pretty simple. So you're just fine with good old Yarn, even version 1.0 Hadoop. On the other hand, if you want a combination of batch and stream processing, you can consider Spark, Flink, and SAMZA. If you're only doing mostly streams, Storm is optimized for that. And then if you want to handle messages, then Kafka. In this batch plus stream, I can also stick Samza right there, okay? I mean, I've already done that, sorry. So those three are for combination, and then this one is basically just for stream. It's the opposite of this. This is only for batch, all right? So again, if there was good old Hadoop right there, only batch, only stream, combination, combination. Cool. How do you fit them all together? These are the stacks, okay? These are the so-called tech stacks that companies have, companies like Uber, LinkedIn. It's so cool, sometimes they give you a talk on like what all this is, and then they tell you. So data sources can be SQL, NoSQL, server logs, Twitter streams. And then ingest, how do you bring all those into, this big world of, HDFS? You can use things like Flume, Scoop, Kafka. And then this is the actual core part, the processing. You can use good old MapReduce, write mappers and reducers yourself. Or you can write Apache drill code, or you can do Spark processing like that. And this is all for this machine learning, job management. Again, SQL, search engine. Oh, there's a typo. SOLR, okay, Solar. It's also a search engine, or Lucene, you can do other searches, and then column databases. And then this is the graph data flow language. So this is the hardcore part of like why you do all this in the first place. And this is the fun part. Now I get to consume the results. If nothing else, you can visualize it and look at it. Or you can do like data mining and machine learning in here, okay? Okay, so then that's one way they can all fit together. There's hopefully like a lot of new things, that you didn't know or you knew part about, but I want to tell it to you all. And then there's a tiny bit more, just the last 4 slides. What it is this is a very different alternative. These are called alternatives, like all these 4 right here in particular, right? All these alternatives. But underneath, they all do the same thing, which is, they're all running on like a Hadoop file system where the jobs are all independent of each other. No matter what you do in this, one job, one mapping job, one Samza task processing is not interacting with another task processing. One mapper in good old MapReduce is not interacting with this mapper over here. They're all separate, and that is where the speed up comes in. But there are some scientific problems in the world where it'll be nice if that is true, but it's not true. Meaning there are things you can do in parallel, but at some point you need to actually combine some of these independent results. And then afterwards you can go in parallel again for a little bit, and then you have to stop and do some swapping of data. It would be when you have a massive matrix that has 1 million by 1 million rows and columns. There are matrices like that in the world like that, by the way. 1 million, look at Netflix, okay? Maybe 100 million users. Each one is like a row in a matrix, okay? Imagine Netflix has 10 million offerings for people to watch. Each is a column. That's a giant 100 million by 10 million matrix. And each matrix element is a yes or no, 0 or 1. Did that person watch the movie? Did Sati watch Game of Thrones, season 1, yes or no? Did Sati watch The Office, yes or no? Incredibly, Netflix actually has data like that. It is insane, right? Every time you go and you turn something on, then they add your data to the thing that they have ongoing. Every time somebody subscribes, they make a new row for them. Wow, it's a crazy amount of data like that. And then they can invert such a matrix if they want. How in the world would you possibly invert a crazy matrix like that? You can actually invert like lots and lots of sub-matrices and then combine them all. You can do lots and lots of data combination. And then in the end, you can invert like a main matrix. There's all kinds of numerical algorithms for that. So how the heck do you, where do you run them? How can you run them? That is called bulk synchronous parallel processing. For the first time, you have a completely new model. This model was actually an old model, like a 90s model. But the computer scientists that came up with it, they're pretty cool. This guy is amazing, by the way, Leslie Valiant. He talks a lot about artificial intelligence. In fact, he's the one that I think I align most with my own way of thinking. He talks a lot about human memory, how the brain works. One of his books is called Probably Approximately Correct, PAC. Okay. Anyway, and then he won the Turing Award, right? Google, the Nobel Prize, rather. All cool stuff. But then the world ignored BSP. The world is like, wow, what do we do with it? It's pretty cool. Google came along and said, oh my God, we should use this. So Google actually implemented BSP, which is cool. I'm going to tell you. So what BSP does is the following. You still have a parallel system, like a Hadoop system. They work independently, right? A lot like Hadoop so far. But after they work independently, they need to talk to each other. And then once they finish talking to each other, that whole combination where they work in parallel and then do some swapping is called a super step. Like one stage in a bunch of processing. That's one super step right there. Work in parallel, exchange data. Then you do it all over again. Go back and work in parallel, exchange data. Second super step. So super step, super step, super step, super. The whole algorithm is done. In each super step, therefore, you got concurrent, local, parallel operation where the memory is all local, no swapping, no exchange of data. It goes very fast. Local memory, local variables. It's asynchronous, meaning they all don't like wait or depend on each other. And then this is the serial part. They all have to exchange, many of them have to exchange data. And so then they send and receive data, message means data. Okay. And then after that, there's a time step when all this is finished. The time step is a conceptual thing. It is called a barrier. So the idea is when the time reaches barrier, all of this communication is done. And then they're all independent again. Then you can start a brand new set of this again. And then you just over and over do these three parts over and over, okay? So those are the three steps again. Local computation, communication, barrier, synchronization. So you have to wait till everybody finally says, done, done, done. There's a lot like the whole distributed, thing that you have to do with transactions, right? So what is that called? Quick, not 2PL, two-phase commit, to PC, right? So like to PC, where the coordinator has to basically wait till everybody says we're all done running, and then you can all run again. That's what this is, okay? Step 1, step 2, step 3. The whole thing is called a super step. And then you can run something similar. All the super steps are not identical, by the way. Now you can run maybe a different algorithm or a different stage of the algorithm. But the point is that the speed up comes when these can all run in parallel. But then they have to wait, like this is done, and then it has to wait till this point, then it's forwarding data. And likewise, this is done and sending data. This is done, send data to this and to this. It depends on the nature of the algorithm. Who knows what they are. But for that, you need that to happen. But you're guaranteed that at this point, they all have each other's data, whatever they want. And then you can now run in parallel again, okay? BSP. Cool. So then Google came along and said, we'll invent a phrase called think like a vertex. So if you are a vertex holding some data, then what are you looking at? You'll be looking at neighbors who are other vertices, they hold data. What if you jump from data to data, vertex to vertex? What if all the vertices can run in parallel up to a certain point? Like each vertex holds a document. Maybe they're all searching for some certain terms in a document. They can all run in parallel. But at some point, they need to put all their searches together to maybe rank the pages. Then there'll be page rank. Then they have to communicate and rank them, right? Because rank depends on how many other nodes are connecting to your node, right? To your document. Okay, that would be the communication step. And then they can all go search again. So Google thought this is a very cool idea, and they made an implementation of BSP called Pregal. Only if you're inside Google, you can run Pregal. But Pregal is basically a BSP implementation by Google. So cool, right? And all these people wrote the paper. Read it. Okay, so the things that I told you here, vertex state machine. It means what operation can run in parallel, okay? They call it a vertex state machine. And then the model of computation. So super step again. So these are all different super steps, you see. So in every super step, they can run in parallel, but then they also have to exchange data, and then that super step is done. And then afterwards, next super step. Combiners, aggregate. So this is all very similar to what you've seen before. It's basically like a superset of MapReduce, where you can do MapReduce with this if you want, but you have the option of different mappers exchanging data to other mappers. See PageRank like right there. So you can go read all this, okay? But it's very clever that you can do so many things fast, and then when you need to stop, you stop, then only exchange data when you want to. So you get speed up. All right. So then they wrote that really cool Pregal paper. Yeah, so why is it called Pregal? Oh my God. Okay, this is very cool, actually, 7:40. I think I'm doing pretty well on time. What the hell? Okay, so let's actually do this thing. Why is it called Pregal? What does the name remind you of? I'm going to start giving you hints, okay? Pregal is the name of a river. It's the first clue. Bagel, I love that. Okay, as cool as it is, that is not quite the answer. Okay, so there's a river. Should use blue, right? Okay, river. There are bridges across the river. Hey, wait. That bridge. One bridge. Second bridge. Bridge. There's a lot of water, A lot of water. And then there's something else over here. Be another body of water. Another body of water. It's a river. What am I trying to get at? river, bridges. The Eagles have a song called Seven Bridges Road, which I can actually sing for you. That's a hint right there. Seven bridges. You start walking and you say, my city is broken up. The city is pretty cool, actually. My city is broken up by using 7 bridges, which I can walk through. I wonder if I can walk through all the bridges. Exactly. Very good. CG got it. If I can walk through all the bridges only once without walking through the same bridge a second time, I'd basically come back to my starting point, which would be like a cool circuit, right? Like a Hamiltonian circuit. Hey, neat. It's basically graph theory, okay? That's what it is. So the mayor of Prigal, yeah, exactly. So the mayor of Prigal, sorry, Prigal is the river. Sorry, I'll back up. Prigal is the river. The city, Königsberg, is where all this happened. The mayor of Königsberg wondered, it's all here. The mayor of Königsberg said to himself, I wonder if I can actually be efficient and not walk through the same bridge again. Stays up all night for days and days and days and try to figure it out on a piece of paper. Could not do it. Mails his Swiss mathematician friend Leonhard Euler. Euler, you gotta help me. What? Can I ever find a path? It's bugging me, driving me crazy. Euler writes back, sorry, impossible. Birth of graph theory, okay, that's exactly what happened. So Euler abstracts all those bridges using little nodes, okay? It's pretty neat, like right there. So like there, all of this, okay? So you can read like lots and lots of things about it. But that is where it came from. Bulk synchronous. Let me see. Okay. Just to show you that part, because I can easily show you a picture like right here. That's what I'm talking about. Okay, so there are the 7 bridges, right? And then the whole Königsberg city is broken up in all these pieces, especially in here, you know, this little island, right? See, the mayor wants to talk to like all the people that live here. Then he said, can I actually have a path that does it? So this is what Euler did. So Euler said, I'll just replace like all of this piece of cities by just simply all these nodes, right? That's all they are. And then each one of those is a bridge. So the idea is, can I walk through, can I reach all of them by just walking through all these nodes only once? What do you think the answer is? Or when do you think it's possible? When do you think it's not possible? Okay, I'll give you a hint. Here it's not possible because I can look at that and just tell you it's not possible. Why? I would look at something different and tell you it might be possible. Exactly, even and odd, okay? That's exactly what it is. So when you have an odd number of, incident edges from a vertex, it is not possible. As soon as I add one more, like say I build a second bridge or something, it is actually possible because you can go through one bridge and come back to the other bridge, okay? Yeah. Okay, so here's what happened in history. The Allies, because of the Second World War, bombed the heck out of Königsberg, unfortunately. So somehow the bridges broke. And so because the bridges broke, now a circuit is actually possible. So please go on Google Earth and see if that is true for yourselves. I've thought of making a homework problem like that, okay? Like do it before and do it after. It's very interesting. It's actually possible. So you can use KML to plot like a little path. All right, so I told you a lot, but that is the reason why, okay, I'll show you the blog post. That is the reason why I didn't go look at the official last line after. Oh, that's right there. Yeah. See that? The graph theory, the whole world of graph theory was actually born because of that, okay? Amazing. All right, so then what does the Apache organization do? They make Giraffe. So they said, wow, the Google can own Prickle. The rest of the world wants the same thing. So they implement the BSP, idea, and then they call it Giraffe, okay? Okay, so then there are others also that do something very similar. They're all graph databases. Hama, Golden Orb, Stanford GPS. They're all for processing graphs, okay? But Giraffe is specifically only for graphs. These things can do non-graph data structures as well. There's some slight differences. So then what is Giraffe? Underneath, you go to a file system. So the idea would be, again, that I have a massive graph that has got millions, if not billions, if not, get ready for it, trillion with a T. A trillion is 1,000 billion, astronomically large amount of edges, right? A graph can be made up of that. It exists in the world today, actually. I think it's in the next slide. Somebody wants to do a graph operation on a graph like that. Oh my God, good luck. Thankfully, you can use Giraffe, you can use Hadoop to do the whole the bulk synchronous processing, right? Because you can operate, like I told you, on different subgraphs, but because edges are involved, those subgraphs would have to exchange data, like say like label propagation or something, then you have to actually exchange some data across those graphs, across the subgraphs, which is when the communication step happens. And then the barrier step, then they can all go off and do more things. Okay. So HAMA again does BSP like that, just like Giraffe, and then it's used for high performance computing, basically scientific programming applications. Okay, like weather simulation, drug design, it's all the usual things, water desalination, disease spread. Okay, so they need like lots and lots of computing power. And then so then just like this in HAMA, you store like lots in memory, and so then it's actually faster than Giraffe. So if you're able to afford HAMA, then it runs on the main memory. But the same idea that it's got a vertex centric computing. So then you have this MapReduce, but then you can exchange data. But you can do other things as well. You can do, for example, matrix algorithms, even network algorithms. Okay, but Giraffe is only for graph computing. I told you that. So HAMA is like Giraffe plus plus. Exactly, very very smart. Zookeeper's job is to keep track of all this stuff. Now you see why it's needed, right? It's too much. That's all Zookeeper does. You're right. Good. Okay, so 1 trillion edges. Okay, and this is not even recent. Now they have WhatsApp, and so like even more people. It's like a few years ago, but back then they wanted to run graph algorithms. These are classic graph algorithms that you read from your data structures, graph class, algorithms, analysis class. But now you do it on Giraffe. So this is a thing on how Facebook did it. 2012. Wow. Now they have a lot more. So everything that I'm telling you is more. So this is what I mean by label propagation algorithm. But imagine this is all one big graph. But you can do subgraphs like these, but then you have to exchange results. Okay. So then they give you some examples. Okay, read the paper. There's a lot of detail that we cannot possibly read through. Same idea, they do some master slave computation, but now you can update across each other. Workers can see like this, right? So you can send data across, and these are the super steps. Cool. See, the cut is graph partitioning. So you can actually do graph partitioning cuts, and you can do like local k-means, and then you can combine them. So split, and then all this results. Okay, applications. There's PageRank, okay, and then there's other kinds of label propagation. Friends of friends, so you can do friends of friends calculation. Suppose I ask you something very simple. In general, what is the friends of friends count? Like for every friend on Facebook, how many friends do they have? That's one total. And then for all those friends, go find their friends. Add all that up. So what is the average of that? Divide by like 2 billion users. That's a massive calculation, okay? Then you can actually do stuff like that on Giraffe. That's what they're talking about here. Wow. Neat. Okay, 1 trillion edges, but now probably like way more than that. Okay, so I talked about a lot. Those 3 are the ones that I just now mentioned. Wait, there's actually one more. Okay, this one. There. Datanomic is a very neat site, by the way. You guys should start following Datanomic, like Data Tsunami. This is a couple more years after that, but this actually talks about what they did there, okay? So more easily readable write-up. So there's Giraffe in 2013 API for graph search, and why did they choose this? What? Look at that. So 126 times faster than doing it like serially. Wow, crazy, right? And then you can read that story as well. 2 orders of magnitude, right? Who gets that? But that's possible. Okay. 1 trillion edges. Oh, we didn't cheat. Okay. And then blog post, and yeah. See, that's exactly the cut right there. Okay. All right. Oh yeah, what is a click? So in a graph, yeah, it is insane. Now it's all even more though. I wish they would update stuff like this. Okay, so what is a click in a graph? What kind of graph is a click graph? A click. How would this be a click? What would I have to do to turn this into a click? CLI QUE click. Click. Right. Combine. It's a complete subgraph in the sense every node should be connected to every other node. So when I have n vertices, suppose n is like 10 or something, how many edges? N of them? Exactly, choose n2, right? So it says 10, then it's 10 factorial over 8 factorial, 2 factorial. Cool, right? Very nice. But that can astronomically grow. So imagine then doing this on like all of Facebook, 2 billion people. You want to find out who's friends with whom. That's like a massively, crazy calculation. So in general, it's a very rough, vague question, right? But it's true. If you want to run like a click operation, or actually, let me ask you a different question. Supposing you have like all of Facebook, right? All of Facebook is not a click. Like I'm not friends with all 2 billion people. Neither are you. But I want to ask a different question. I got like all this crazy graph, but I want to ask how many clicks are there of size 4? Like this, that means how many groups where all the 4 people are all friends with each other? Maybe there's one over here. These 4 are friends with each other. These 4, these 4. I just want to count them. Such an algorithm, what would be the running speed? It's a very general question. Because then I can ask, are there clicks of 100 people? Are there a group of 100 people, maybe they went to school together, or a small town, where all the 100, each is linked to other 99? How can I find that across all of Facebook? It sounds like that'll take days and days and days to run, right? If you don't have any parallel processing. Those are almost like the n raised to n algorithms, okay? Like order n raised to n. Wow, these are the most compute intensive algorithms in the world, right? Not n squared, n cubed, those are very cool polynomials, right? But it's still pretty bad. Or not log n. This would be wonderful to have, like log n and log n. But these are like crazy, n raised to n. Wow. Okay, or n factorial, I mean, this is still just as bad as n raised to n, right? Like factorial running time. So that's exactly what these click algorithms are, which is why n raised to k, exactly for k click. So as k gets large, you can imagine, right? N raised to 100, 2 billion raised to 100. Oh my God. Okay, so there's just no way that you can do it all with serial machines. You need these massive infrastructures, which thankfully we have. You can go read this. Okay, cool. And then you can do it per continent, if you want. Wow. We actually got through a bunch, and I definitely want to start some data mining. We'll take a break at 8, okay, and then we'll come back at 8:05, because then I can ask you these questions. Okay, so you see, now the whole story is right here. Hundreds of millions of data, Hadoop MapReduce, Hadoop. Oh, I see. Wow, that's so interesting. That's actually cool. So one of the students wrote to me and said privately, in SQL Server, you get faster results. That's a very cool observation, right? I would say, yeah, it depends on the structure of the data, actually, like how many columns you want. Say you have like hundreds of millions of rows. It doesn't mean NoSQL graph databases are always the right answer. And so companies tend to be surprised because you want to jump on the bandwagon and say, wow, Facebook is using it, so we should also use it. Then you try to spend a month and you do it. And they say, what are the numbers? And then the programmers, data engineers sheepishly come and tell you it's actually slower than what we had before. What? Well, do it again. Let's make sure. But that's actually what it is. So these things really actually pay off, for very specific kinds of data. And the companies that do them, obviously this is what they've figured out, meaning this is what works for them. But it might not work for everybody. Marketing data, again, is so much about recommendations and other people and, like eyeballs and influencers. Yeah, exactly. You have to know what you're doing. I like that. You can even do combinations, some marketing data, the social part of it can be done on a graph, but other analytics can still be done on like relational databases. Okay, so we should actually start this. This is fun. Data mining. Even before I start, I can tell you, there's almost no difference between data mining and machine learning. Basically close to zero difference, and I'll actually explain what I mean. In many blog posts and even books, the textbook might say Introduction to Data Mining. And inside, they'll start listing machine learning algorithm, ABC, what. They're pretty much synonymous, okay? They're the same thing, okay? But I'll tell you what the difference is. Little difference. They're same because in both of those, this is like BI, business intelligence, you're looking for patterns in data. In machine learning, you're looking for patterns in data, and the machine learns patterns. Machine learning. When I have x-axis, time, y-axis, amount of money my company made. Over the past 50 years, approximately ... every year, time goes x-axis, money goes y-axis. Amazon goes up, 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 almost like in a straight line. Almost a straight line. Then I give that to a little machine learning algorithm and says, hey, find that line equation. I have a slope, m, I have a y-intercept, c, and my line equation is y equal to mx plus c. But x is like time, and then y is like billions of dollars I make. I literally learned the line equation. Then I can tell you, I meaning the AI, so-called AI, can tell you, I'll predict in 3 years how much more money you're going to make. Jeff Bezos says, okay, tell me. Then what the software does is plugs in for the X value 2023, 2024. finds y equal to m, because m already knows, right? Times, 2024, whatever time unit was, 1, 2, 3, 4. Plus c is some $100 million, adds it, and says at this rate, if nothing else changes, the world doesn't blow apart, no earthquakes, nothing, no terrorist attacks. This is the amount of money you're going to make. And why not, right? Because the past told you exactly what is happening. That is all machine learning is. I'll trivialize it for you. And I think, oh, come on, this is glorified line fitting. Then I'm going to say yes. And your point is, yeah. So I tend to make fun of machine learning like you wouldn't believe, but hey, I'll justify it. You're learning, the machine is learning patterns. So otherwise, don't be fooled by the word learning. It is not like you're learning to ride a bike or doing something pretty cool, right? It doesn't do any of that. It's pretty dumb, actually. And it works because of past data. It's very simple. So one of my most favorite books in the world, which I'm going to give it to you as a PDF that you can read over the break. This can change your life when you're young, you read it, which I did. It's called Zen and the Art of Motorcycle Maintenance. It's a beautiful, beautiful, beautiful philosophical book. It's written by this guy, a mechanical engineer from MIT, so he knows what he's doing. And it is about motorcycles. He and his son go on a motorcycle tour. Say this is US, okay, this is US. East Coast, here we are in Los Angeles, Midwest, Ohio State, Iowa. This is the upper, like a Western US, Montana, Wyoming, Idaho, North Dakota, South Dakota. They go on a motorcycle tour, a loop, a circuit, like right there. So this book is a travelogue. See, there he is. That's him and his son. So it's beautiful. I've read this book too many times, and it's just wonderful. Talks about winters, open roads, and the freedom of a bike, and just on and on, right? Mosquito repellent, right? But you will learn so much about mechanical engineering. You will also learn so much about this word called quality. What is quality? This is a good quality course. That's a bad course. This is good quality food. That's a bad quality motorcycle. What the hell is quality? That's what this book is about, okay? Specifically, he answers the question, is the quality like a subjective concept? Is it in your head? So somebody else might eat the same food and say, oh, it's horrible, but you think it's great. Is it in your head? Or is it in the food itself, so that anybody that eats it would say, wow, high quality food? So which is it, subject or object? I'm not going to answer it. You can read it. But it's a great, great, great book. It does end sadly, which I won't read now. And then the author passed away a few years ago. He got old. But it's a great, 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 great book. You should absolutely read it. So in the beginning, it talks about patterns, okay? So it shall actually get to here. Right here. You look at where you're going, which is the future. Never makes any sense. Like you don't know what's going to happen next year, right? The pandemic is just going away. But hopefully you can look back, right? Hindsight is 2020. You remember your past. And then the past, you can connect the dots. So maybe you're on a trajectory that goes like that. And then if all else remains the same, you're going up like that. Or maybe your past trajectory looked like that. So now you're up here, almost inevitable that this is going to happen. You should prepare for it. That's what this is, okay? So all of machine learning, all of data mining is about that past data. Because by definition, that is all you have. You have no such thing as future data. Future is not there yet. So how can you use the past to analyze the future? Data mining in one line. If you analyze the past and explain the past itself, like why the hell did we screw up? Why is our money, why is our income going up and down? Like what do we do wrong every year? Like what the hell, why is it happening? Then that is basic old-fashioned backwards analysis, okay? What is called predictive analysis is for the future. Then you say, if that is going on like that, then I should expect that to happen. So you can analyze the past or the future, but same math, same everything. Okay, then what is the difference? In data mining, you do the analysis yourself. You run the line equation and you tell the machine, thank you, and I have my line equation. And then you become the expert and you can predict what's going to happen. Whereas in ML, the algorithm says, just ask me, I'll tell you. I'm intelligent. I'm as smart as you are. And that's all. No difference whatsoever. Same algorithm, same result, same equation, same model, but who is using it? Too simple. So data science is the science of data mining. Is the science of extracting, again, useful information from old existing large data sets. BI, right? Same as BI. At the heart of it is the process of discovering relationships. Any relationship between, piece of data is like a pattern, right? Some kind of pattern. Upward pattern, downward pattern, oscillating pattern. No pattern at all. It's also a pattern. So large observational, meaning pre-existing data sets to find unsuspected relationship. If all this is so trivial, you wouldn't even talk about it, right? But somehow the relationship is inside. It's not so obvious. In 2 dimensions, if I plot X versus Y, I can just take a look at it and say, wow, it's going that way. If I have 100 dimensions, meaning I have even more columns of data, then the way all the data is actually laid out in 100-dimensional space, we cannot see anymore. That is when you have to rely on things like, dimension reduction, right? And then SVM in like multi-dimensional space. So the math gets more complicated. You cannot see it. But otherwise, the idea is like dead simple. You're still doing the same thing. You summarize the idea in novel ways, understandable, useful. Okay, data mining exercise. So what you get from the result of any data mining algorithm, any machine learning algorithm, is you throw the data away and you purify it and you build what is called a model or a pattern, okay? The equation, the line equation. Like I give you a bunch of x comma y dot dot dot. You join them. Hopefully they're in a straight line, first of all. So I join them and the correlation is very high, meaning they're almost a straight line. Then the result line equation is called a model. The model generated the data, okay? The data led to a model. In other words, the reason why it went like that is because of some underlying phenomenon that happened. Maybe Amazon hired the best product managers. So every year they know what they're doing. So they're making more money for the company. There's some reason why the data looks like that. And then you call that reason a model, okay, or a pattern. If the x-axis was time, and you call the whole pattern, the model, the relationship, call it a trend. The trend is that over the last 10 years, the amount of plastic water bottle usage in the world is going down because young people don't want to pollute the environment. So at this rate, in like 20 years, there'll be zero water bottle usage. So a trend in time, or more and more people are becoming vegetarian, vegan milk, and all that, right? So that's called a trend. Trend means the time is the x-axis. Okay. We'll take a break soon now. Be like a couple more slides. Okay, then how is ML different? I told you. ML is different because now you have a so-called algorithm, which is the same line equation finder, but you call the model finding training. Training because it does not know X is connected to Y. And if you give it only one data point, there's an infinite number of lines that pass through, the one data point, so you don't have a model yet. When I give you 2 points, maybe you can draw a straight line, but the third point might be over here. So the more points I give, and if the points are all like one straight line, or maybe a slightly curved parabola, maybe the points are all going like this, then I can fit a parabolic equation. It just depends on the data actually. Okay, so then if I do that, then the machine is being trained more and more and more. And finally, the machine is done learning the data. The data is very complicated. You cannot do simple things like line equations, parabolic equations. The data has crazy non-linear patterns in it that we cannot see anymore. That is when you would use a so-called neural network, which is still all those neurons, which are just simply like linear equation finders. Each neuron is finding one linear equation, believe it or not, okay? But then it takes the linear equation and tweaks it and makes it a tiny little nonlinear equation. It's called the sigmoid. You already probably know that. So when you put a whole column and a whole bunch of rows all together, then every neuron is making a little tiny piece of a linear equation and then making a nonlinear piece of it. Then you combine all of those, and at the very end, the softmax that you have on the right-hand side, wow, that is one giant equation through all the input data, your 100 billion, piece of data that you have. One giant, horribly complicated equation. But in the end, it's an equation. That equation is what would be called a model. In the self-driving car example, believe it or not, the entire traffic data that you had from the past 10 years all became one giant equation in the Waymo car. And then you put the car on the road and you turn it on and you sit down. You don't drive anymore. The model then guides the action. The model tells the car, there's somebody crossing the road, you got to stop. There's a red light, there's a stop sign. You need to turn the right signal on, make a right turn. It's all being learned from pre-existing data. So no data, no machine learning, no AI, no nothing. It's gone. That's all it is, okay? Okay, so in the end, now you know, and I'll keep insisting that it's an equation. I think in my last homework, at least last spring, that's what it was. I made the students actually write the equation out. I gave you a tiny neural network and I gave you data. And I said, first of all, fit the data. That was easy. Then I said, what is the equation? Many students, said, why do you make us write the equation? That's boring. Well, do it anyway. And finally, they all realized, wow, it is an equation after all, meaning it's a model. It's y equal to a whole bunch of, M1, M2, M3, M4, because there's X0, X1, X2, X3, X4 is multidimensional. But in the end, it's an equation. Those equation coefficients, those M's and those C's. The M's are the weights for each neuron. When a neuron learns a weight, you're actually solving for the slope, believe it or not. When the neuron has what's called a bias, that is the C, the y-intercept. Wow, that's all it is. And then there's so-called sigmoid at the end. You don't need like a separate M or C for that. Then you understand, oh my goodness, the entire thing is ultimately fitting some kind of crazy line, and then makes the line be nonlinear. And so that is the good old world of ML. So I summarized ML for you. I think we can stop by mentioning the following. Right. So then the point of all of that is once you find the model, right, some new unknown value, some new value here 10 years from now, I'm going to ask you, what is the Y value? So you plug into your equation that you found and you tell me what the Y value is. A new traffic, data, meaning I go on a new road. But then you look at all the new traffic patterns and you ask, what should I do? Still the same equation, okay, same plugging in that never, ever, 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 ever changes. That is called supervised machine learning, what I told you. The supervision is this part. You take your old data, your existing data, and then you fit like a model through it. That's called supervising. And then the machine supposedly becomes double quotes intelligent. Ha. My calculator is also intelligent, I had to realize it. Well, if you call ML intelligent, yes, my calculator is intelligent. This course is the one that kicked all of this off. And this guy is really is the one who made machine learning a household name in the world. Because back then, 10 years ago, probably longer than that, his course at Stanford was still machine learning. He opened it up to the world. He went on the internet and he said, oh, that's cool. Wow. All this comes like, full circle Coursera. They called it MOOC, right? Like massively online, course, right? Online offering course. So then thousands and thousands of people signed up because they were fascinated by the word machine learning. Wow, I get to, find out how a machine learns. Then he starts off with statistics, as usual. It's all here, by the way, the whole course. Okay, see that? So then people think after 2 or 3 weeks, they go, oh my God, this is like effed up. Why? I hate math. There's a reason why I'm an artist, dude. I hate it. Okay, well, I'm teaching you math right here. Well, then, F you and F your course. People started dropping, okay? All those people that all dropped. At the very end of the course, only a few hundred remained, okay? And they got like a completion certificate. But meanwhile, the damage was done, so to speak. People thought, wow, machine learning. But then what you don't realize is it's good old statistics, okay? And combined with some probability. He didn't do damage or anything, and I'm not saying that it's all like bad stuff. But then, he, I think inadvertently made it be more of a cool thing than it really is, because it's not, okay? It is standard. It is what it is. But in the meanwhile, the world got seduced by like all that. Okay, then it moves on. Then it became like, then a few people started this company called Coursera, and then they obviously, like list a lot more courses. And then that is pretty cool, right? Like public, neat, IPO. So anybody that, like invested there are going to become like billionaires, including him. And there's no doubt, this is good stuff, but it is classic math. So you can go read everything. So maybe look with a new eye, what I told you, it is all great. There's nothing wrong with it. But in the end, there's a model generation. You can call it a model, right? Yeah, super models. Okay, we should take a break. I talk so much. Why don't we take a 3-minute break? I won't even go anywhere, but just get some water, go to the bathroom and come back. And then we'll start, okay? I want to ask you some questions. I'll at least stop this. Okay, almost back. We'll wait till a few more seconds, and then we'll officially start at 8:12. I'll ask you some questions. Let's do a little discussion. Meanwhile, thanks to Karishma, I looked up Coursera just now. Cool, because I was not aware. Let's start in a few seconds. And 2, 1, 0, start. Okay, so check this out, right? This is like top stories today. Very interesting, right? This is a company that a lot of people know about, and they have high quality courses. So there it is. Whoa, all these IPO thingies. But the backstory really is this: in the early 2000s, the Department of Defense, they had these competitions, these self-driving car contests, where they would say to universities like Stanford, you can have a self-driving car, just set it up with your grad students, and then see if you can drive. Oh, so sorry. Wait. Thank you. I'll just back up and told you what I told you, like right there. See the Coursera IPO, right? 6 billion, not bad. Very nice. Okay. And so all this. So what I was going to say was that these things, Coursera, like all the basically a little bit of a hype about machine learning came from the following. There were many reasons all that happened in the early 2000s. One was a self-driving car contest, that the Department of Defense would sponsor. And then Stanford was actually one of the, entries all the time. There's someone called Sebastian Thrun, Thrun Thrun. So Thrun and his students would compete, but the idea was to drive from like Palo Alto all the way to Las Vegas. That's always the course. But then most of the cars never even actually got off the Bay Area. They'll just go off on the side of the road, right? Go in the ditch. But a few cars just kept going and going and going. That is where the self-driving idea was actually born, when people realized, maybe this can actually work in the real world. Okay, so that came from there. And likewise, this course started, and so a lot of people talked about, wow, we'll have AI someday and they'll rule the world and robot overlords and all those memes, right? Which is all not true at all. And then because it's linear algebra is not going to take over the world. And then the third thing that also happened in the early 2000s is GPUs. So GPUs are pretty powerful. We use them in graphics processing unit. But then a few people realized, graphics people do matrix multiplication. Every light source, every camera is a vector. And then every rotation, every scale, every translation I do on my video game, on my object, on my ball, is actually a matrix. And I'm doing matrix times vector multiplication. Vector is input data. Matrix is a neural network. So I'm multiplying data by a network and I'm updating the weights. So it's the same calculation. Then people said, wow, give us your GPUs. So then machine learning got a huge boost, okay? And so these all happened. And so that is the reason, yes, RTX 3080. Sure, very cool. So NVIDIA now is a top company. In fact, before I forget, I'll mention GTC. That's the last thing I'll say. A confluence of factors that all propelled machine learning to basically, the stratosphere. And I will tell you today, 2021, right? Things are actually down more to a reasonable level. Some people might even think it's a bubble that's about to burst, okay? So I won't basically burst any of your bubbles. But I've followed AI for the past almost 30 years. So I'm going to tell you with a long view. So it was hyped up to be like way more than what it really was. And so, but the reality, sinks in. Anyway, so Andrew Ng was at Baidu, the Chinese search giant, right? And then he's back now in the US, I think he's back at Stanford, actually. Okay, very cool. That's like one of the big reasons why all this took off. But I want to ask you, let's stop here. We'll do all this next week. Let's do a little discussion based on like MapReduce stuff. It'd be neat. Okay. Go here, 11 here. Okay. Let's go backwards actually, because then when we run out of time, we'll just finish. So Musketeer, and then there's Kafka. How would you think that they're similar? I'm actually asking you, like, what are the similarities? I won't mislead you by saying they're not similar. They're actually very similar in one very important aspect. What is it? If you remember Musketeer, yeah, correct. Musketeer is the one that takes all the front ends, meaning all the graph specification languages, and then all the back ends, which are the cloud platforms on which Hadoop runs. And then rather than write like an M times N driver, they make an intermediate graph representation language and translate the front ends and back ends to that language. So it's an indirect layer, right? So how is that in Kafka? Like, what is the indirect layer? Like, what are the two sides in Kafka? Kafka is what you call a pub sub, exactly. So yeah, the publishers and subscribers, right? It's the data providers and the data consumers. You don't want them to directly be wired to each other. So you want a level of indirection, which is actually what the Kafka's core is. They maintain a table, like a routing table, that says when this publisher publishes data, who are all the subscribers that need to know? Then we'll just send the message to them and point to all the partitions and records. So they both involve a level of indirection. Okay, so that is the answer. Good. So then what is the benefit? So what is the benefit of doing the whole pub sub? The idea is, it's again one of the oldest ideas in computer science, the whole notion of loose coupling between components. So what is the advantage of loose coupling? Right, so both of those actually, fewer translations, higher reliability. So it is just the idea that then each can then be independently updated. They can come and go. One of them can morph into a different service or something. But as long as the channel signature remains the same, it doesn't matter how the actual Twitter message comes in, as long as I can always extract the tweet, who tweeted it, what time, what place, and what, then that is all matters. So you can have loose coupling, because then you can change the architecture, but then things still keeps working. Yeah, right. Then what is the difference between like Java versus Java and or Python MapReduce versus doing PigHive, meaning this is one bucket, this is another bucket. What is the difference between this bucket versus that bucket? Like this way of doing things versus that way of doing things. Simplicity, correct. So can you elaborate on that? It's a good answer, but how else would you qualify it? It's simpler because of what? I would still ask you. Not integration. Maybe now you're getting a little bit colder. It is simpler, but what like what sense? Built on top of that. Correct. Correct. Um. Hmm. Yeah, that is also correct. So you guys all, definitely are saying the right things, but then maybe there's one reason for all of that in a way. Like, what is enable? Yeah, exactly. So pig does the work for you, right? I mean, that is the main thing. In other words, conceptually, you don't worry about mappers and reducers at all. Okay, that's the painful part. That's assembly level programming. I would rather think in terms of a graph. I would rather tell you, take this paragraph, take that paragraph, and merge them together and combine, translate all the verbs and pull out all the adjectives. I'll just tell you what needs to be done. The how, you figure it out. So I'll tell you the what, you do the how. What is the high level? How is the lower level? So we program in a higher level, and that's the abstraction. Higher levels are always simpler, okay? Because I don't need to give you all the detailed directions. That is why. That is what explains like all of this lesser code. These are the side benefits of all of it simpler, because you don't have to worry about the details, okay? Exactly. So it's implementation. Yeah, correct. So conceptually, I'll tell you what to do, but then you know what to do. So I won't even bug you. It's up to you. Good. Yeah. So data flow. So again, how is the notion of data flow related to all of this? So again, in a data flow architecture, you have nodes. Nodes are just simply code that processes, data, but there's many of them. They're all connected together, and then data goes into a node and gets processed and comes out, and in turn enters a different node, and that node would then have to update the processing that it does and then send out data. So data just travels between all these nodes. So how is that related data processing? It's like almost what we answered, but what would you say? So the data that is being processed, it starts out as the input data that the user wants to analyze. It's all the mountains of data that we have. Then the processing consists of doing all of these calculations, like word counting or doing the linear equation, slope finding, anything at all really, neural network weight learning. So the idea would be that each node does a little bit to the data, and as the data travels from node to node to node, what you finally get on the output would be the result that you want. For example, the machine learned model, or the line equation, what. So each it's like a staged processing. Okay, so each stage does a little bit of the processing, and overall you have this pipeline. But then what travels through the pipeline is data. Okay, they're like function calls, but you don't call them function calls. More like a graph. You're like executing a graph is really what you're doing. Right, sure. It depends on the flow. That is correct. Which is why in LinkedIn, they treat them both identically. They tell you after you read the batch, after you read a file, it's as good as a stream because all those words in the text files went into memory, right? And streamed directly in memory. So, but the idea is the flow. Okay, so data is what flows. And then you have a graph to flow the data through, and each node in the graph is doing something intelligent. So at the very end, when all data flows through, finally when you're done, something useful happens. That is how these ideas are related. Meaning, data flow is much older than big data processing, but big data found a way to use a graph as an abstraction to describe all the operations, every data mining, every machine learning algorithm, and their combinations, like ensemble machine learning. It's just one node that actually gets the data from so many other nodes, and then it combines them. So when we come back next week, I'll go through all of that, okay? But then you can think of what you already know in new ways, okay? And then this, I think, I already told you. It's 8:21, so we should probably stop. All right, cool. So do we see you next week or not? We don't. I can ask my supervisor, really. Yeah, that's actually true. So I'll tell you what, Dense staff, he gave me a very cool little deal. If you guys give me even 5 extra minutes, we'll go through a little bit. So I ask, and if they say no, then it's no. So thank you, Dense staff S. Awesome. Yeah, I'm actually not teaching 571 next time. It's back to Marco, and he actually also teaches it in the fall. This is cool. I'm glad that they offered it. F571 is a very cool course, you guys. It's actually a complement to a lot of what we do here. All you have to do is just simply change the URL. Okay, so this is all it is. I'll leave it up here. It's being recorded. So I have like very similar things in here, but I highly recommend it. Okay, there's like lots and lots and lots of neat things here because all the data stuff that we talk about have all turned into what are called web services. So the most amazing way to program anything in the world today is to think of every server as a node. So I talk about graph, right? Imagine all servers are actually nodes in a graph. And then each node gets data and then sends something out. And how do you run a node? It's an API call. Oh, thank you so much. How long can I go? Maybe another 5 minutes, you think? Wow, that's so sweet. I appreciate it. Wow, cool. 8:30. Okay, 7 more minutes. This is great. Okay, so this is highly relevant. I'm going to tell you. You send data to a server using a question mark after the end of URL. It's that simple. Then the server can do something to your data and send you results back. And then you can then take the data, send a different URL to a different server. So you can treat all of the servers as nodes in a graph. Oh my goodness, that is what this is. So like that, okay? That's called a microservice architecture. And this is the most general thing that we have today, the REST architecture. So yeah, highly, highly recommended because it'll then tie all these ideas together in a very beautiful way. Hey, thanks, Saurabh. Oh, that's neat. Okay, so a tiny bit more then. SIMD. So then what is the deal with SIMD? So I talked about SIMD. So what is SIMD and how is it useful in big data? S is single, M is multiple. So what is SIMD? SIMD concept is you take a certain instruction, right? A single instruction, which is your map function. Then you run it on as many chunks of data as possible. Yeah, Hamza is absolutely right. That's the multiple data part, meaning these are all fragments. And this is my map function. So I'm running in parallel the same map function on all the fragments. And yeah, that's exactly. Yeah, vector processors, the old fashioned, I told you, Cray, YMP, they all had vector processors. So in Fortran, there's what's called parallel for, pair for. So in pair for, when you have an array full of things and you want to do something to an array, I can treat all the array elements as if they are parallel. And so in the time it takes to update one element, you can update all of them. But same kind of an idea, okay? So in this case, you call them mapping. Each element would be mapped to a different processor. Okay, very cool. And then functional programming languages. So why is functional programming related to big data? Again, what is the connection there? This is not something new, by the way, just we talked about it, but then how do you remember? Data values can't change. I'm not sure if you're answering the question I asked you. Stateless, sure, but more to the point though. There are functional constructs that are specifically used in big data processing. There are two functional constructs, very specifically. Yeah, these are all true, but two functions, exactly. Not filter, but map and so map, exactly, reduce, correct. So map is one function, reduce is the other function, okay? Those are from functional programming. And then we found ways to, use them in big data processing. Very good. Okay, so this could be useful because we talked about triple store, and the whole knowledge graph idea. When you combine a whole bunch of triple stores, the resulting database is called a knowledge graph. These days, Google search engine, Bing, they all use it, okay? You can take Wikipedia and so many sources and make a knowledge graph. Say Los Angeles, it's like a city in California. Then somebody searches, for something in LA, right? What is LA's population? Then they go in knowledge graph also and know that LA is in California. So they'll give you a little box that says LA population. And then they might say other big cities in California, San Diego, San Francisco, whatever. Why do they know that? And how do they find out? Because they're using a knowledge graph. So knowledge graph can be used to augment things like search results, okay? So that's what all this, hey, I worked on that. Oh my God. Okay, so knowledge graph has a very interesting past. I have a lot of mixed things to say about it. I worked with this guy 9 months. That's for another day. So the idea is you take all the knowledge in the world and you combine them into almost like a class definition. This is not where LA is a city in California. It is more like US states have US cities. It's abstraction. Then you instantiate this abstraction and you get things like, Manhattan, so place in New York. Okay, so anyway, this is also for another day. It's a knowledge graph, okay? So knowledge graph idea. And this is exactly what I told you about the whole triple graph, okay? So Barack, was born in Honolulu. When I went to Honolulu, the person that hosted me took me to his apartment. He lived on a second floor, and he said that's where he and his grandma lived. Okay, so Honolulu is like a city in a state of Hawaii. Now you see how they're all wired, right? And then here's Michelle. See, they met, married to. And then she lives in the US as well. Then you can keep going. So please read about this. It's very fascinating. Microsoft had a graph called Cairo, and then now you come to the 2000s, meaning so many people have wanted this and reused it over and over. Now search engines use it all the time, okay? It's a nice history of knowledge graphs. But I want to claim a little piece of history to say, hey, as only as it started. In fact, that's the first entry. What the hell? I'll tell you that story another day. Okay, so knowledge graphs, and then we still have 2 minutes thanks to the generosity. What I want to show you is, again, 38 minutes and 4 minutes really fast, okay? In other words, please watch this, but I'll tell you why. This is a nice introduction to the whole world of NoSQL databases. But the very first, few minutes, the 38 minutes, are like an intro to all of it, meaning the 4 types.
Good morning to everyone on the West Coast. Good afternoon to everyone on the East Coast. And good evening to everyone joining us from...
And good night to people in China. Okay, so then you've got 4 SQL, NoSQL categories. Then you got like, this is actually very cool. Like data size versus, types. So like here, key value can handle unlimited data, but it's very simple though. If you want complexity, you have to go to graph. Okay, so just keep going like that. It's a good introduction. And then there's the graph data, the things that I've talked about in the past. This is all using the Matrix movie, okay? And then how you can query this using good old Java. You can actually do classic Java, or you can use Cypher, or you can use Tinkerpop. So 3 different ways to go into.
An interesting thing to note about working with Neo4j.
Okay, so it keeps going like that. I told you the first 38 minutes because it still is pretty useful. Then they tell you. So these are the queries you want to make, and then you can go in the graph and actually make queries. Because the graph it can get quite complicated, right? Like this.
Essentially, what you want to do here is you want to start at the first node with Thomas Anderson.
Okay. And then this is still Java. You can write your own traversal functions that intelligently know what to do. So if you get a hold of Neo4j, you can do all this yourself, actually. It means you're given a standard Java-based graph data structure and all these Java classes and methods. And so you can traverse it however you want. So you don't need Tinkerpop, or Cypher or anything. But you can always use those as well.
What if you want to do another type of query that says,
okay. So then,
and then you get it.
This is all you can skip, okay? Then they get pretty deep detail into all of that. That's why I told you, then do the very last, So jump to 1 hour, and then the 4 minutes at the 1 hour mark, okay? Like in here. It's all towards the very end. Like some of these, see, like right there. I'll stop with this.
A node like any node, which then has another relationship to node that's called friend of friend.
You could do a very similar thing, right? If you want, so there's Gremlin, so that there it is. Do it in Gremlin as well. Or you could do it in good old SQL if this was a table. Okay. So that's all about Neo4j. Anyway, so please definitely go watch it, and then you're going to learn a lot more, okay? All right, so now I think we can then. 571 is neither difficult nor straightforward. I'll tell you what it is. It's a ton of work, because we'll show you a video where we nitpick and tell you exactly how many pixels make up that button, how the scrolling works. And your job is, when you do your homework, to exactly replicate it, or you're going to start losing points. And initially, it's a ton to learn. Like a pretty heavy ramp up where you learn these front-end frameworks like Angular, or a backend framework like Node.js. But that you can do, actually. You can allocate some time. But then it looks scary. It's the only way that I'd put it. So if you carefully do your background studying and maybe come up to speed on things like Angular, React, Node, then it won't be like so bad. So of these, I'm going to say it is straightforward. Difficult would mean even if I tell you like how to do it, you still would not know how to do it. Like some cool algorithm that I give you and then ask you to compute the running time. It's not like that at all. It is just simply that the ideas seem like straightforward, but it takes you like a hell of a lot of time to actually get it right. Yeah, so definitely go here and basically educate yourself. All right, thank you, Sarah. We can stop. Goodbye, everybody. We don't have class next Wednesday. It's a wellness day, basically spring break part 2, day 2. So please goof off, have fun, and then see you like a Wednesday after. Garim Havinish. Tata. Okay. Goodbye, Tian. Awesome. Srirag, Srabi, Hamza, Malaki, Harsh. Srirag again. Bye-bye. Aryaman. Akash. Anyone else? Okay. Have a good night. Stop share. Leave. Vaishnavi. Bye. You're welcome.